you, Gamune.
Okay, very good morning to everyone here. Today we are going to do our fourth session of embedded system for beginners. Before going to that, I would like to say thank you for ENTC for the collaboration, and also for the participants. We hope that you got so many things during these past weeks, and today you will get valuable time. You will spend valuable time during today as well. Also, I have few notices. With the SLInspire program, along with the program, we have organized A-level guidance program for students who recently got the A-level results and who are going to apply for university entrances. So along with that program, we had two sessions. First one was the guidance for the form filling, that UGC entrance form, and also the next one was general session, how you should choose a university course and along with your career. And also we are organizing another few sessions according to this subjects, the streams that you have faced for the A-levels exam. So I would like to invite you to stay tuned with the SLInspire social medias to get know more about that. Before going more, I would like to invite our speakers to start the session.
Thank you, Dilini. Am I audible? Hi. I think okay. Thank you. So I think we are ready to enter the last week of the workshop the Embedded Systems for Beginners workshop, and very glad to see our participants joining us for the last week as well. Let me get started with the last week's content. First of all, today we'll be discussing 3 sections, and we'll be firstly touching upon firmware uploading to the Medibox and about Microchip Studio. The second topic would be in-depth microcontrollers, and both of these topics will be covered by me. After that, Abharajitan will be doing an overview of embedded C++ programming, and Dr. Subodha will be closing the workshop series today with his introduction to embedded system design. So just to give you a heads up on what's coming up, this section on embedded C++ programming has been like scheduled around 10 a.m. and Abba will be discussing some key topics of embedded C++ programming. So like he has prepared some great content, and he has expanded it up till custom library development, and I believe like this part is very crucial, very valuable for all of you to get familiar with. And so I want you guys to like stick around till this point, and also at 12 p.m. onwards, Dr. Subodha will be doing this very exclusive part on embedded design flow, and this he has like prepared some great advice and content for you guys. So those who are interested, please do stick up till that point. Right. So let's get into it. Right. So week 1, all of you worked with Tinkercad, and I believe Deepan and Charlotte helped you guys to get started with Arduino programming, and we designed the Medibox device like this, right? On a simulation, and using the breadboard, and we came up till this point. We uploaded the entire Arduino program, and we got this kind of an output, and we showed you guys how we use the Medibox. Week 2, you guys developed the schematics, the layout, and also the PCB on the ECDA online platform. And you learned about how to interface a microcontroller, do the connections and configurations, and we didn't go much in depth into this part, but still we managed to route a decent PCB, and we were able to like get the components 3D models onto the PCB and look at it on a 3D setting, and that was pretty interesting, but still we haven't touched the real world. In week 3, we taught you guys how to develop your PCB, that is to fabricate it or to realize it into the real world, how to do best practices and further design considerations. And I think Deepan and Charlotte also discussed a few techniques you can use to do this kind of a PCB at home, right? Now, week 4 is the very interesting week where we bring everything together, and we do the uploading part. We are going to upload firmware, that is our Arduino code, Arduino program, onto the Medibox, and we are going to see how it's going to be done. And as you can see here, this is a picture image of how I uploaded the Arduino program, and you can see that the simulation of week 1 has been done here, right? So let's go ahead and see how I did this, and you guys, all of you guys can do this exact thing. Since all of you have followed the Medibox design flow, you can go ahead with this. So required resources, you have to start with these things. So the USB ASP programmer is shown here, and here is the pin connections that are relevant for your Medibox program. So this is the USB ASP interface, and there are 6 wires here, 6 connections, and those 6 connections have been highlighted here, and you have to connect them correctly according to this pattern. You can see that the wire comes from this side and the red wire is on the top, so it's on the VCC side. So do the connections correctly, and you have this reference of the Arduino platform just to see like which connections correspond to the Arduino connections, because you're using Arduino program. If I were to show you the Arduino program that you guys were using, yeah, I think you can see the Arduino code. So in this Arduino code, you have set these pins to the LED and the buzzer, and the I2C library has been included, and the LCD has been created using the I2C library. So those are the, and these are the 4 buttons actually: A0, A1, A2, and A3. So you can identify that requirement when you go through this pinout diagram. You can see here A1, A2, A3, A4 correspond to these pins, and those are these connections. That's like you can see here when you go through the schematic, right? So those are the required resources, and there are a few steps that you have to take care of before you go ahead and do this. So these are like I did this myself. So these are my like advice tips on how to do this, and I'd like to advise you guys to do the same. So I've listed the links that I found online that give this advice. So when you connect the USB ASP device to your computer, it's going to appear on under device manager, like it's going to detect a USB device connected, and it's going to appear like this: other devices USB ASP. That means that the drivers are not installed. Like when you connect a USB to the computer, you need the supporting drivers to communicate with it, but those are not installed. Therefore, you have to get it up till this point. You have to install the USB drivers, and you have to get this kind of a connectivity to the USB-AC, right? The thing is, there are few drivers that are available. Like when you download this software called Zedic, there are few drivers, actually 4 drivers that are available. And the trick with this is, like not every driver works for everything. Now, what I found out was for the Arduino ID, libUSB-K and WinUSB are the 2 drivers that are working. So if I were to let me open that software. Um, so I think you can see this screen, and I'm going to connect my USB ASP to the computer. I'll show you the USB ASP in a while. So when you connect it and you select USB ASP, you can see that replace driver is there because I already installed the driver. However, there are 4 drivers here, right? WinUSB works with Arduino ID, and libUSB-K works with Arduino ID. But WinUSB doesn't sort of support Microchip Studio. That's those kind of issues are shown in these stack exchange ones. And this libUSB Win32 works with Microchip. So what I found out is like the best thing you have to do is you have to install libusbk and then replace it with Win32, or you can do it the other way around as well. Install this and replace with this, and that's how it gets supported to work with both of them. You have to do a combination of this, like so. Keep that in mind, and we'll go ahead with this section. So now the drivers are installed, and my USB ASP is recognized. Just to like show you that it is recognized, I'm going to open the device manager, and here you can see sorry, yeah, here you can see libusbk USB ASP. So that's recognized there. Um, yeah, okay, right. Uh, yeah, so next up, you have your Arduino program ready, and so I've already developed my Arduino program here, uh, and I've done the necessary additions that I require. And in Arduino program, you have to select your programmer as USB ASP here. It's normally it's AVR ISP is the default programmer, and because like we are installing it to the Arduino Uno no, most of the time, so even the board you have chosen will be Arduino Uno, but that is fine. You don't need to worry about that. Only USB ASP you select, and here you can select the option upload using program. Okay, so I'm going to click that. I'm going to keep it there, and you can see that my code is compiling. So it is a similar gif of what's happening when I do this. Right, so it's writing, it's uploading now. Okay, yeah, it's done. So my code is completely uploaded. So this setup works, and I hope it works for you guys as well. I have included my medibox.ini files and like all the resources in the resource folder, Google resource folder. I think I'll put a link for that in the chat in a while. So all of you can download all the resources I'm using in this section today, and you can follow these steps and get this up and running. Right. These are some slides from our first workshop where Deepana and Shaluta sort of went through the requirements such as like when you're going to make this physically, about including the I2C liquid crystal library, and the wire.h is the I2C communication library. So these things you have to go through and revise. That are the program slides from 17 to 23, and just get an idea about what you're putting into your firmware before what the firmware that you're putting into your Medibox before you sort of test and see whether it's working correctly. So I did that, and I did all the like debugging parts correctly, and this is the final output. So yeah, it's up and running. I got the welcome to Medibox screen. And I got the test set time screen. I'm going to do some button pressing. Right, so you can see that when I press the right button, it's going to switch between. Yeah, and I'm going to go to the set alarm mode now. Before that, I'm going to check and see what the current time is. So when you press that button, you can see the current time. And then I'm going to go for set alarm. I'm going to set hours. So this is pretty cool, right? Like 4 weeks, throughout 4 weeks, we went through the process of designing this. Thankfully, we didn't make any mistakes, but we have gotten it up to this level, and the alarm is set now, right? So that was what happened with the Medibox, and I hope all of you will be able to get it up to this level. Since like we have provided all the resources, all of you have the capacity to do this, any questions or anything you have on this these things, you can always contact us and ask us, but I would like all of you guys to come up to this level. Now the additional approach that so the additional approach that we want to leave you guys with today is the Microchip Studio. Now this is a very important tool, very like professional tool that we recommend you guys to use for projects starting now, like early onwards. And it's the same as Atmos Studio 7. Microsoft Studio is the same as Atmos Studio 7, but it's just a renamed version of it. And you can use the same online resources to learn about this tool. I have drop the link of getting started with Atmos Studio 7, and please download this. I have like left the downloading software as well on the Google resources. You can go there and get that and download this and install this software. It uses Visual Studio to actually run, but I think that will not be an issue for all of you. Right. Now this is the program that we're going to do today. Blinking the LED and the buzzer. I think you noticed that in the demonstration I just did. There was no like LED or buzzer movement, buzzer activity, and I don't want to leave you guys thinking that it's broken or messy or anything. It's working. So I'm going to prove that that is also working in the circuit. And to do that, we are going to develop a small program to use those two resources. So it's going to be done on Atmos Studio, Microchip Studio, and it's called the Blink program. So this is my program. I've also left this program in the Google resources folder. So download this, and here you will, once you open Microchip Studio, you will find the main.c file, which contains the code that we are requiring today. So these are resources on the code. So just let me go through this code what we are going to do today. So here's a small snapshot of our schematic, and in this you can see that pin 13 and 15 of the microcontroller are being used by the buzzer and the LED. And this is actually, if you consider the microcontroller, I'll show this diagram. It's actually in 13 and 15 now, TB1 and TB7. The same thing is mentioned here. Okay, so 1 and 7, and that's PD7 and TB1. So what I'm going to do is I'm going to first define the clock frequency, and that is 16 megahertz. That's the clock we use. And afterwards, I'm going to import these libraries that I want for the project, like the delay library and the input-output library. So I need those two libraries for the project. And afterwards, I'm going to, in my main program, that is the main, I'm going to first initialize. I think this is sort of like corresponding to how in Arduino we have this void setup and void loop. So that's sort of what's here as well. You can see int main and while one is the like how it's working on embedded C++. It's not the Arduino similar thing, but you'll be learning about these things in Abbas section actually. So yeah, this atmel start in it already comes, and then you do these two lines to define port D1 as the first digital output and port D7 as the second digital output. These two lines do that. So you have already set them as digital output. Now in your loop, that is the looping code or the void loop or whatever it is, you're going to first write two lines that turn the port high or the pin high up to 5 volts, and now again turns the pin low, and there's a 1 second delay between both of these. So you have to see, like when we do this, we have to be able to see what's going to happen. I'm going to show you through the webcam as well. And right, so let's get Microchip Studio here. Before I explain this, I'll just do the demonstration. So I hope you can see the Microchip Studio screen. And in this one, yeah, Microchip Studio screen is here. So in this one, this is the program and everything's there. And I'll explain about everything in a while. So first, what I'm going to do is I have my this thing connected. So I'm going to just let me see. Yeah. So I'm going to webcam off. And let's remove this filter. Right. So I hope you guys can see the. Just can someone let me know if you can see the microcontroller on my webcam? Deepana, can you let me know if it's visible?
Yes, we can see.
Okay, thank you. So now what I'm going to do is going to build my program here. Okay, and build this succeeded. That means that it's compiled correctly. And what I need to do is and tools and just go to USB ASP. Right, I'll teach about how to set this up, but this is going to, and when I do this, right, it's working, right? Yeah, you can see that. So this is how I program the Medibox using the Microchip Studio, and this can be extended up till any like project you are working on. And I would like all of you guys to follow this in the future, right? So I'll get back to this. Okay. Right. So yeah, now that's done. Okay, I'm going to remove the limits now. That's box. Okay. Right. So yeah, I think that part's done now. The only thing that we haven't discussed is how to do this, like how to set this up, and that was a bit of a like complex situation. So I'm going to show it through this GIF here. Now you open Microsoft Studio and you load this main.c file, and I have explained what this code is doing. And before I go into this setup, there's this, yeah, I'm going to build the code like that. And since you're going to use the USB ASP in external tools, you have to add USB ASP like that. Okay. And once you add USB ASP, you have to, in command, you have to put this software called AVR. I have put the file as well in this location. You have to give in under external tools, you have to give for the third space, you have to give this argument, these two arguments in the required locations. And here this PM332P means the microcontroller that you are working. So for AVR Dude, is a list of valid parts that you can use, and M328P stands for Atmega 328P. And once that is done, and your output directory debug file target name, that is this particular file, blink main.c, in under blink you can see the debug file, and in debug file target name.hex is the file that you want to, like the hex file is what you want to put into the microcontroller. So that's what it is doing. It's using the USB ASP connection to put the hex file into the microcontroller. And this is the project directory. It's not much of an issue. And I've prepared the links of yeah, few links of the relevant things that you might, sorry, here, sorry, right, this is where you can download the AVR Dude software. You can go through those different things right now. Yeah, everything's in the Google resource folder, so you don't have to worry about actually downloading any of these things. I've provided everything in the resource folder. Right, so just go through these links and learn more about what's happening. But I think so far it's okay. Covered everything. The last thing is just to give a small heads up about this soft tool and what's actually here in terms of usability, user interface. So this where you program, and you can always go and start a new file. Either you can start a project file. You can choose G++ static library project, or create a project from Arduino Sketch. Those things are available. And you can either start an Atmel project, right? And in Atmel project, you have to choose the microcontroller that you want to work with. If you go to create new project, it will allow you to choose the microcontroller. I choose the Atmega 328P. And this is the first one is what you need. I'll explain why. The PDIP 2828 pin package is what you are using. And this is the microcontroller that you are working with. There are other versions of 328P, but those are not the ones that you are working with. And what else? So this is the debug section, and here when you're building your program, sorry, what happened? Yeah, I think the debugger. If you select simulator, you can debug your program, and if you have errors in your program, the debug pointer is going to show those errors in that section I showed you. This is the X program, I believe. Yeah, and this is where you have all your files your ink files. I think I will go through this in detail later. And your util files, and src is your main files, and the main.c also has your like main Atmel files, right? That's a small coverage about that software. It's a great software. I think it's really cool. Definitely good to use. Right, now to move ahead with the rest of my section. Um, so today we are going to discuss a bit about microcontrollers and go a little bit in depth that we didn't do so far. And I think all of you are quite capable now with the knowledge you have to ask questions and process this content. So we discussed what a microcontroller is in our section in week 1. But here's a nice diagram to show what goes into a microcontroller. Microcontroller is a small computer on a single integrated circuit. I'll show you a nice diagram containing a processor core, memory, analog to digital converters, and programmable input-output failforwards. So you can see that this IC, which happens to contain an oscillator, is actually integrated inside the microcontroller. This A to D converter is contained in the microcontroller. The microprocessor can also be integrated into the microcontroller as in the form of the CPU and the memory and those contents. The RAM can be included into the microcontroller, and program memory, and all those different ICs that are doing dedicated tasks have been integrated into one single chip called a microcontroller. So it's absolutely amazing, what a microcontroller carries, like the capabilities it carries. And if you see this diagram here, I think this is not the Arduino that you are familiar with, but don't worry, because it's still the Atmega 328P chip that's on the Arduino. There's just a small difference between the chip that you are familiar with and the chip that's here. So the chip you are familiar with is a dual inline package DIP. I just showed it to you on the Micro Chip Studio, and it has 28 pins, and it's a through-hole one. And this is actually the number that I told you to select on Atmel Studio when you were working with the USB SP to program the Medibox. But this particular chip here is also Atmega 328P, and it's actually having a different packaging. It's called TQFP is the name of the packaging, and it has 32 pins, even number of pins on each side, and thin profile plastic pod flat package is the name of this package. So it's an SMD based package. So it requires SMD based techniques. You have to be quite experienced. I've done it myself. You have to practice to get good at SMD. So SMD based package is used in this particular Atmega chip, and we're going to see what's this little part here. So this is the Atmega 328P chip actually, and what you see here is everything that's in this particular diagram. So this is the Atmega 328P, what do you call the diagram, like the system architecture of the Atmega chip. It's got all these data buses running around, the SRAM, input-output ports, EEPROM, flash, all those different things that are contributing to this microcontroller is inside this chip. This is really amazing. It's a complete system on a chip, and I don't know which sections are which, but you can actually this might be the program memory. This section might be the the RAM or something like that, and the CPU might be somewhere here, and its units somewhere here, and then the bus architecture running somewhere like that, and this particular this particular field is called analog IC design. It's very interesting field, and I hope some of you get to go into this area one day just to study about this area. Yeah, it's very fascinating, right? This is the Atmega 328P chip, and it's called it's actually a silicon die. It's called a silicon die, and it's fabricated on a silicon wafer, and you just cut out silicon parts like this, and you put those inside chips, and you make these kinds of chips, right? So that's how that happens, and that Mega 328P is now different. It's done like that, right? So so that above thing, once we generalize it, we come up with something like this. This is the overview of components of a microcontroller, and inside microcontrollers in general we find a set of components: the central processing unit, which ranges from like 4-bit to complex 32 or 64-bit processors, very powerful processors, and then there's the data storage RAM, the EPROMs, RAM is for random access memory, and then ROM is for read-only memory, and EPROM is for erasable programmable read-only memory, and EEPROM is for electrically erasable programmable read-only memory, and then the flash is also there for program memory, and this is for storing program and operation parameter storage. Then we have serial input output pins. Then there's the universal USART, and then other serial ports like the SPI, this serial peripheral interface, and the I2C is another serial communication channel, and those are supported on modern microcontrollers. Almost all of the microcontrollers have this now. And then peripherals, timers, PWM generators, watchdog timers, internal clocks. So those kinds of like specific things are now also there in microcontrollers. Maybe yeah, like these ones here. And the last part is the analog digital converters. I think in microcontrollers you see in the Arduino that analog digital converters are allowing you to get data from the real world, like analog domain, and then convert them to digital signals, and do like things with it. So those are supported by analog digital converters, and even those are now in microcontrollers, like at microcontroller level. So it's very amazing, like what microcontrollers have turned into. And for any microcontroller, the most important document that you would have for any system on chip, the most important document is the datasheet. It's a very long document, around like 300 pages long. I've like worked with datasheets, and there's even though you still run into problems, like datasheet has almost 80 to 85% of the answers. And here you can see that in our particular Atmega 328P microcontroller, it's an 8-bit microcontroller. So that's about the CPU, and 32 KB of programmable flash memory. That's the programmable memory statistics. And you can see 1 byte of EEPROM, 2 KB of SRAM, 6 PWM channels, 8 channel 10-bit ADC. So there's like a 10-bit ADC which you can use on 8 channels, and SPI serial peripheral interface, USRT programmable serial USRT, which is what you use on the Arduino to program it. Actually, like use upload code to the Arduino. Actually, that's what you use, and interrupt and wake up on, and timers are there. What else? Yeah, I think like a very powerful tool, right? You can see that just by looking at it. It's a complete computer. Like if you have heard about computer architecture, you can sort of relate to this, right? Complete computer on a chip. And here's this diagram. It is actually at the end of the this sort of in the start of the data sheet. This is the end of the data sheet, and you can see that the diagram specifying what the chip looks like and the scaling and everything. This is important information when you are going to design PCBs. So from the start to the end of the datasheet, you have all the important information, and you have to like learn how to read datasheets. I'll show the datasheet in a while. This Atmega 328P chip and the Arduino actually has been an important topic in our discussion in this workshop series, and we now that you have come up to the fourth week, I would like to invite ask you guys to learn more about the Arduino now, because maybe you knew that these are the analog pins and these are digital pins. There are two serial pins like that. You knew about that one, but now you are ready to analyze the Arduino and learn about how the analog pins work, how the digital ports work, how the ADC is being used for analog to digital conversion, and what else? About the system clock of the Arduino, how it works and how the timers are functioning, those kinds of things, and the communication ones. I also want to provide some content on this ones for you to study, but given the time constraint today, I won't be going into theoretical depth of those contents, but I'll try to provide them in the drive or through via email if possible in the future. So yeah, these are the links, the learning resources on microcontrollers and on general. So please do go ahead and study about these things and get a fundamental understanding about how microcontrollers work and what are all the concepts related to microcontrollers that you want to study about. Okay, so here this is actually sort of to complement the previous slide. So this is the Atmega 320 SND chip now, and it has 32 pins up till 32 here, 1 to 32, going like that. So you can see, if you take from this dot here, and one starts here, and then goes around like that. And these kinds of diagrams are very important because they're showing you what the capabilities of the microcontroller are. This is basically the most important diagram you have to work with when you're starting with microcontrollers. Like when you're starting to work with microcontrollers, this diagram is your main reference, and when you're going to design something, you have to understand how many analog pins you have, how many ADCs that are available to you. Here you can see ADC 0, 1, 2, 3, 4, 5. There are 6 ADCs, and then you have to understand how many pins work as digital pins and how many pins work as so these 4 pins you need to put into the USB ASP interface, so you can't use them. So you have to keep those pins aside, and the Nextel1 and Nextel2, those are the crystal pins, the oscillator pins, so you have to keep those aside for the oscillator. So when you're routing also, you have to think about these things. The oscillator has to be close to these 2 pins. Those kinds of information are on the datasheet as well, so please refer to the datasheet when you're doing these kinds of things. And then these 2 pins are for the UART communication, that is communicating with the computer or some other device, and the I2C communication. So you have to keep those pins aside for those kinds of work. And what I'm going to show you next is what happens when you start like that and when you get into the project. So here you can see the schematic diagram, and in this schematic diagram you can see sorry, I think this yeah, I'll remove that later. So here every microcontroller can be initially completed up to a standard level, and here you can see that this is a completed microcontroller, right? And I have set away the USB ASP connections like that to the USB ASP connector, and then I have routed the VCC pins like that to the VCC connections, and the reset has also been properly routed. The reset is connected to this pin, but it's also connected to VCC across 10K resistor. And then the extal 1 and 2 have been properly routed to the 16 megahertz oscillator, and that's also done. So this is a schematic diagram of the Atmega 328P actually. And here you can see, here in this, like this section area here, you can see all the pins that are available for the user. So microcontrollers enable, like they have a great freedom to enable the user to adjust all the connections he requires and the input output configurations according to his requirements. So the ADCs, the I2Cs, and these serial pins, and other like specific pins. So you have these ones available for your task. So that's how you like work with microcontrollers. You get started with microcontrollers. And other than that, I think some of you had asked how do you like interface these capacitors, which one to choose, those kinds of details about microcontrollers. And there's like, you can't like generally say this is how it works for every microcontroller, because like there are different ways that these have to be done. And it's not complicated. It's not like you could say like black magic, that these kinds of concepts are studied, because there are things called application notes. Now this is a particular application note by Microchip, and it's about AVR microcontroller hardware design. And in this particular, I've dropped the link of that one as well. So in this particular document, you can see all the design considerations you need to do for AVR microcontroller hardware. So in like projects online in the internet, you can find such resources. Like if you research around enough for a concept that you're working on, that somebody else has worked on, you can find all these kinds of resources on the microcontroller interfacing and things like that. And then like there's like tons of like pages of application notes on things that you want to do with regard to microcontrollers, and like official websites. So this Microchip website contains all these like resources. If you take one of them, getting started with SPI, there's a application note on how to get started with SPI for AVR microcontrollers. Selecting the right battery system in the cost-effective manner. Getting started with RTC, real-time clocks. Getting started with Bluetooth, application design guide. So these kinds of resources are like the most important ones. Otherwise, like there's no way to teach electronics and how to place resistors and capacitors for each of these particular events, because it's like too much to like cover in one particular course. But the professional approach is to do this, to learn how to read application notes and apply those knowledge to microcontroller design. And just to introduce guys to what's out there, as a Sri Lankan, I believe these are the most reliable or reasonable microcontrollers that you could work with, that you should gain experience with. And pick was actually, this is how I learned. So I think and most of the people I know also did this. So we start out with PIC microcontrollers, but those are a bit outdated now, and maybe most of you have not even heard or used this. But then we have the AVR microcontrollers, and they have like 80 tiny, 80 mega, and 80x mega. So I don't know where this is, but this is in the Arduino Uno, and this is in the Arduino Mega, right? So these kinds of microcontrollers very famous because of the Arduino platform. And then the last one, the STM32 microcontrollers. And STM32, I fully recommend. These are 32-bit Cortex microcontrollers, and a huge community and huge support, and various kinds of things you can do with it. Like the for STM32, there are like ultra low power, high performance, mainstream ones. Like F1 series is mainstream ones, very popular, and then F4 series is high performance. I've used both of those, and very efficient microcontrollers. And then in the ecosystem, you have the STM Cube, evaluation tools, security tools, embedded software. I don't know the rest of these things. And then for solutions, you can program artificial neural networks onto the microcontroller. Voice and DSP communication properties are there. Graphical user interface support is there, like any kind of touchpad or anything, motor control support, safety aspects of microcontrollers, then connectivity, wireless connectivity for like, IoT applications, and digital power optimization. Those kinds of concepts are there. All these things are available for this community, and you can do all of these things with microcontrollers. And just go online and search for STM32. There are workshops available, and there are like YouTube video series available. Like it's a fully open area platform, learning platform. The community is really great. So yeah, that's about microcontrollers, and I think there's more to learn in this area, but if you like pursue in this path continuously, if you like learn, keep learning, and learn how to do SMD programming, learn how to interface, learn about the communication protocols. These two chips are interfaced with SPI communication platform, and you learn about optimal electrode placement and things like that. You can like this is a project I did, and you can come up to this level. You can do an hardware microcontroller based hardware design project with an STM32 F series. This is a high performance microcontroller, and this is a dual sided PCB, and it's completely, this dual sided PCB is completely routed myself, hand routed, manual routed actually, and completely soldered myself as well. Like every single part was soldered by me using SMD soldering techniques. And I think all of you can see like how interesting this is, and how I believe, like I hope all of you are like enthusiastic to do such a project like this, because for me, like the highlight of my engineering undergraduate life was doing this project. Like for you, this 4 days of the workshop, the highlight would be to develop your own Medibox and program it and see it working. So I showed you a video of mine working, and I hope you guys will do a video of your one working and share it online, and or share it with us as well. Please do share it with us as well in our community and the group, the Facebook group. So the highlight of your microcontroller journey should be this point, coming up with a microcontroller design of this level, where you have done research, and you have gone through lots of advanced ideas to come up with your own microcontroller PCB design. So there are lots of more topics to be discussed, and since this workshop series wasn't enough for that, we hope to bring those concepts in the future as well. And I'll do my best to come up with those sections on microcontroller component area in upcoming weeks, if with the time I have. So that's to thank all of you and to end my section. And I believe Abba is here. Let me just check. Yeah, Abba is here. Hi, Abba. You can hear me?
Yeah, I can hear you.
So, right. So let's hand it over to Abba to do like an amazing session on embedded system design. Take it away, Abba.
Yeah, so thank you, Kidman. All right, guys. So one second. Okay, right, guys. So good morning to all of you. Right, so there are about 100 people. All right, so yeah, this session is on modern C++, and I'm Abba. So I'm a consultant at ENTC University of Maratua. So I was a former lecturer, as well as I'm working in a company as an engineer. All right. So the whole idea of this session is to give you an understanding of the C++ features which have been introduced after C++ 11, that is from 2011. So yeah, so let's dive in. And to begin with, these slides are available in the workshop folder. So we have over here. So you can go over there, and there will be a lot of code, and I will be uploading the code to GitHub before the end of the workshop. So during Subodh's session, I will upload them, and I will put a link. Yeah, so you can go through them. So this one is going to be more of a demonstration where you can like watch and learn, and make sure to ask a lot of questions. Okay, so make sure to ask a lot of questions. So please visit this link, and yeah, so be ready. I'll be looking at the there. All right, so let's go in. Okay, so before we start, let me create a poll. All right, so I have launched a poll in Slido. So please go there right now to this address. Right, so this one, slido.com/47612. Please go there right now. And yeah, so please answer the question so I can get an idea of like what you are familiar with. All right, so if you are not familiar with any language, please mark none. Right, so this is to get an idea of like where you are, all of you. All right, so while you answer that, I will go explain I will tell like what this is about. And I think Kidman might have shown you these slides already in this session. So a brief idea. All right, so there are some misconception about like C++. So that is like some people think it's kind of outdated. So now we have like modern languages like Python, which is like very easy and widely used. And we have like stuff like JavaScript, which like everybody is learning and everybody is doing in web development. So like that, there are like, and almost like every couple of months there's a new language being created. And so like given all that, a lot of people have an idea that C++ is kind of going out of style. All right. So initially I want to like clear some misconception. So C++ doesn't have any competitor. So it is still going very strong, and it will be going strong for the like foreseeable future for several decades. So there's no loss in demand. The reason is like it is the go-to language for embedded systems and for video game development and for desktop software, desktop or like different software like say Photoshop, Microsoft Office, the one we are working with right now. All these are made with C++. So the reason is like all right, and even so especially video game development. So all the high-end the games you play, you download and play the like mega games, all of them are made with C++. And the reason is like it has a zero overhead. So we will see like what that is. So it is like extremely performant. So it's very like highly optimized. So like the programs you make with C, C++, so you get like the the maximum optimization, and the compiler will do like most of the job for you. So it will optimize it like so much. And at the same time, it gives the full control to the programmer. So you can go and you can like change the bits in the memory yourself, and you know where the objects lives in the memory. So like everything like you can do it yourself. And for an example, GPU programming. So these machine learning libraries and everything are made with C and C++. So like you have CUDA, so which like runs on GPU. So all those are like made with but it's like an extension of C and C++. So CUDA. So the reason is like it gives like a very fine-tuned control. All right, and because of that, there's no real competitor for C++. And what are the problems? Okay, so the problem is like it has a very ugly syntax. All right, so we have to admit that. The reason it may not be as ugly as Java, but it's still ugly. So why? Because like C is backward compatible. It has to be by design. So that is from 1970s. You have like I think 70. So around that time you have C, and so C++ is designed to work with any C code. So that means like I think for the past 40, 50 years software, you take any of them and put it and run in today's compiler, it will work. All right. So they have to keep all the old syntax and all the old methods and everything. They still have to keep it. They can't remove it. So because of that, it has a very ugly syntax, and they have to create new and new like syntax to add features, and that is kind of convoluted. And the other problem is like it is too much features to remember. So that is like that's actually a real problem. So which is why the projects like say operating systems. So Linux is written in C. So they don't use C++ for Linux. The reason is like C++ has too many features, and it's very difficult to wrap the head around it. So C is like a very small language, so people can understand easily, and they can write good code very easily, better than C++. So like that. But so C++ has too many features. That's a problem. But that's why it's ideal for game development. So like game developers, like you have to hire a lot of them. So and you have to work very fast. So because of that, like it's good. And also it is very easy to write bad code, all right, because of all this extra stuff and ugly language and everything. All right. And it's difficult to debug and maintain. So those are some problems. But given all the problems, like you have, it's extremely highly optimized. And then in 2011 came the C++ 11 standard, and it took a couple of years to get accepted by different platforms. And after all that, so now you have like a much better version of C++, which we call the modern C++. So 11, 14, 17, now we even have 20. Okay. So and some of them are not widely accepted yet, but they are being accepted. But C++ 11, which we are going to look at today, it's accepted everywhere. All right. So and what are some features like you have in Python? I think a lot of people, 81% of you have coded in Python. All right. I don't. Only 16 people have answered. Can rest of you answer quickly? There are 117 people. Can you please go to this link and go to the polls and answer your programming language quickly? All right. So yeah, then okay. So yeah, so people who have used Python, like we like Python a lot. We love Python. So the reason is like you have very lovely syntax. Okay, so you don't have to think too much, and it's like it's beautiful. And one of the reasons is like you have all these lists, dictionaries, and everything. So you can put stuff into them, take stuff out of them. So like that. And C++ have similar features, what vectors, lists, where you can dynamically add and remove. Then you have like a lot of other features as well. All right. So this is like yeah. So this is like a bunch of different features in C++. You can see like to do the same thing, you have like 100 ways of doing it. So which is why it's a kind of a complicated language, right? So other than that, it is like very flexible. All right. So I will just leave the slide here, and this slide will come at the end also. And you don't have to read and understand this right now. So here the basic idea is like so this is a Python code, and there is a C++ code, and both are basically the exact same thing. Okay, so it's like a line by line translation between here and here. And so I'm trying to demonstrate that you have a lot of features which are common, like the features we like in Python are here also. All right, so we'll go through it, and we'll see what they are. All right, so before that, like maybe a small like a small thing about Arduino bootloaders. So this is not about general modern C++, but I think like yeah. So Kitmin might have done a demo on like how to upload things into Arduino or what into ADML chip and everything. So then some of you might have a question like, so the Arduino has an Atmega 328P chip, but like you can buy an Atmega chip separately also from the shop, right? So can I use that chip as an Arduino? All right, so can I make my own Arduino and use it, or else can I use that chip as an Arduino? Like in case if the chip in Arduino gets burnt or something, can you replace it? All right, you might have a question. Then the answer is like you can, but there's a big but. So that is like Arduino bootloader. All right, so this is a special piece of our software which is there like flashed into the ADML chip in Arduino. All right, so it's a piece of extra code. And so in the memory, there's like a small part inside the program memory, so which is left as the boot flash section. And that has this, all right, so that has the bootloader. And what happens is like, if you take a normal simple Atmega chip, when you power up the chip, it simply runs the program that is inside. Okay, so the program inside will be like a very simple main function, and there might be a while loop or something, like a very like AVR C++ function. So that like that runs automatically. And if you want to program it, if you want to reprogram it, what you have to do is like you have to put it in the reset mode, and it will reprogram. So that's what the ISP does. Okay, this one does. But like in Arduino, when they made Arduino and when they sold it, so they didn't want people to go through all the hassle. All right, so people, they wanted plug and play. You just plug it to the computer and program it. Right, so they want it to be easy. So to make sure it is easy, what happens is like so Arduino has this bootloader software, which when you connect it, whenever you switch on Arduino, or like whenever it gets powered up, the Atmel chip gets powered up. It basically looks at the serial port whether you are uploading a sketch, right? And then it takes it. If you are not, then it will run the code in the memory. So that's like a small extra piece of software that is bootloader. You can actually flash the bootloader to any Atmega chip, and you can convert that into an Arduino chip. So like you can do that. So in case your Arduino chip gets burnt, you can throw it out, buy an Atmega chip, and you just program flash the bootloader, and you can do that. So here's a tutorial on how to do that, so you can check it out. All right, so now let's get into C++. All right, so I was going to show a hello world program. All right, so all right, keep asking questions, and please give feedback here. All right, so okay, so I was going to show a hello world program here, but then I thought okay, like that is too simple. All right, there's no point of showing it. So instead, this is like a quite simple program, and what we are doing here is like All right. So what we are doing here is, let me demonstrate the program first. So you can get an idea. Okay, so I'm going to run this program. Okay, so if I run the program, then it basically asks for okay. If I run the program, it asks for my name, and if I say bar, and it asks for my age. If I say 26, it tells me so I am Abba and I'm 26 and I can vote. All right. So it also asks for yeah, it also asks for my hobbies. So if I say my hobby is like say programming, camping, and something like hiking. All right, and it remembers that and it tells me back. All right, programming, camping, and hiking. So it asks for my name and age, and then it tells me back. So that's what it does. And if you look at yeah, so it's a very simple code. So like to explain it, what happens is like okay, when the C program starts, it always starts in this through the int main function. So we call that the entry point for control. So what is control? So control is like a small yeah. So control is something we think that flows from the top to bottom. All right. So wherever that goes, that code gets executed. Right. So it's a construct we come up with to understand to visualize these things. All right. So the control actually starts from the main program, and it goes there and there and there. And if you have a function, then it goes through the function and comes out. If you have a loop, it goes again and again into the loop and comes out. So that's a control. All right. So the control starts with the main function, and the main has to be int, but the return is optional. All right. So you can return a number, or else you don't have to. So if you return, we usually return 0. So that tells the operating system that it's okay. All right. So everything is successful. All right. Then optional, and this is the variable declaration, the way you declare a variable. So here I have int age. I have declared a variable, but I have not initialized it. All right. I have not given a value to it. So this is a common mistake. It's not a mistake if it is intentional, but it's sometimes it leads to bugs. So the problem is like when you say int age, what it does is in memory, it takes a small 4 bytes and names it age. All right. So, but it does not it does not assign any value to that. So which means whatever the value there in the memory will be a garbage value. It doesn't mean anything. All right. So it can be a very large number like 10,500 or something. Okay. So it will be a garbage value. And yeah. So to avoid that, what we can do is you can initialize it while declaring it. So you can say this one is a char array. Greeting is an array of welcome. All right. So that's how you declare arrays. All right. So when you do this, it gets initialized also. All right. So yeah. So that's a difference between declaration and initialization. And in Python, you don't have that problem because like whenever you define something, you always initialize. So it's a equals 5 or something, and the 5 goes into that. But here you can declare, but without initializing, right? Okay. So what is this? There are 2 types of strings here. Okay. So that's something I wanted to show. So one is what you have. Okay. So this is just a typo. I'll fix that. So this is a C style string. Char greeting is a C style string. It's basically an array of different characters. Okay. And then, but that is not preferred. The second one is preferred. So this is a standard string. We call it the standard string. It is inside this standard library. All right. So you have to, it is in the standard namespace, and you have to include the string library to use that. So that is like a bit more flexible, and it has some advanced features, and it's much better. You can pass it into functions. You can do those kind of things. So I always use this. Okay. So don't use that one. Always use this, the second one. All right. So but the first one also can be used. That is like backward compatibility with C. All right. So you can do that. So this is console output. If you want to print something in the console. So in the program you saw that I printed name. So this is how it got printed. This is console input. So when you type the name, it goes in, and when you type the value from the console, whatever you type, it goes into the variable age, console input. All right, and then I'm printing the name and age. Okay, and this is a condition: if else and if else, if else if and else. So yeah, you can do that. And so this is a function. So this is what we call a function definition, like where we have defined the function, and that's what we call function declaration. All right. So now this is not necessary. Function declaration is not necessary if you put this function above main. So when you compile it, like it understands that this function is there. Then sometimes we don't put it above main, and sometimes we put this in different files. So if you have like too many functions, you put that in different files. I will show you one example. And when you do that, you have to declare this. Okay, so you have to tell the compiler that there's a function like this somewhere. So then the linker will go in, like it will find the, like it will get compiled separately and it will be put together. All right, so that's how it works. All right, so you don't have to do it if you write this this code above main, but because I have written it below main, I have to tell that this function is there. So that's what I do there. All right, so this is the function call. So like it's just like any other language. And so this is okay. So now here, this is a namespace. So here std is actually a namespace, the standard namespace. So what is a namespace? The namespace is like you have a bunch of say names, that is identifiers, functions, and those kind of things. They are defined inside that. All right. So I think in many examples they just put using namespace std here, and if you do that, you can use the cout and cin and everything without writing std cout. All right, so here I have written like that because I have written using namespace std. Okay, because I'm using that. Now it's like I have imported everything from this namespace to this scope inside here. So which means like cout and cin I can use without telling it's std. It knows. But that is not a very good practice to import all namespaces like this here and there. So the problem is like sometimes you might define a variable or function, and that might collide with a function's name that is already inside std. Okay, for an example, if you can't say something as vector, all right, because vector is there in std, and then so like you can't say something in list. You can't name a variable list because it's there in std. It will give a lot of errors like that. So because of that, it is better to just restrict the usage. So like inside a small scope. So what is the scope? Is between these braces. So between that, I'm using this one. Okay, that is just to show you like it can be done. All right. So this is an array of objects. Okay, so that is a normal array. It's an array of char, and this is also similar. So this is an array of object. So there are 3 string objects here, and we will see how to make objects and everything in a moment. All right, so that's a for loop. And so, okay. And this is a range-based for loop. So what is that? In Python, you have this like very nice syntax of for element in list. Okay. So then like you don't have to say for I in range something, and then you list I, you don't have to do that. All right. So you can just say for element in list. So that is very nice way in Python. And in C++11, they have introduced that to C++ also. So you can now say like for hobby in hobbies. All right. And what is this auto? So auto is something like I will explain later on also. So auto means like here you have to type the data type's name. Say into here, what is a hobby? It's a string. So you have to say string here. But you don't have to say string, because if you type auto, it will automatically understand that it's a string. How does it understand? Because hobbies is a string array. It knows that. So then every value of hobbies will be a string. Okay. So then it knows that hobbies will be a string. So now in this place, like you can just say string, but the idea is like if you have like very long names. So like I'll show later. If you have like that kind of long names, though, you can use auto. Okay, to keep the code readable. So otherwise, like it look very ugly. All right. Then you have, okay. Right. Okay, so that is this is basically preprocessor directives. Okay, so include and include. Yeah, this include is a preprocessor directive. So what does that mean? That means like this IO stream is a header file. Okay, so somewhere there, and it has a bunch of code, bunch of C code. What happens is like when you say include IO stream, all that code it is processed by something called the preprocessor. All this hash statement, hash include, hash define, and all of that, they are processed by preprocessor. So preprocessor is something that runs before the compiler. So when you say when you compile it, like when you write C code and when you select run, the first thing that runs is like basically something like the preprocessor. So preprocessor, what it does is like it just copies everything inside that file and pastes here. Okay, just copy paste. So it doesn't it doesn't do anything. It's not smart. It's very dumb. So it will just copy and paste everything here. So like that, we are basically copying everything in this string file and pasting it here. Everything in IO string file and pasting it here, and then it compiles. Then this file gets compiled. Okay. So this include, that's what it does. All right. So okay. So this is like a summary of all these things. Okay. So all right. Yeah, preferred. And okay, you can say braces. Now, for an example, here in the for loop, I use braces. In this for loop, I don't use braces. So why? If there's only one line, you don't have to. If there are multiple lines, you have to. All right. So I think a lot of people know that. Then you have like a function signatures. Function signature means like the return type, function, and the argument types. So for an example, so this is a function signature, void. So get this one. So void means it doesn't retain anything. That is a function, and like it doesn't have any arguments also. So now this entire signature is unique for a function. What does that mean? Means I can create another function exactly like this, and I can change, say, int get show hobbies. Okay, and then I can say what return an int, and if I do that, that will be a completely separate function, although it has the same name. Okay, although it has the same name, it will be a different function. And so like that, if you change the argument type also, like it will become a different function. So which is why like you will always get some errors. So this so this type of function is not there. And if you get an error, the reason is like you might have changed the argument type or else this type. Okay, so yeah, so the entire signature should be unique, not just the name. All right, and this auto, it can actually make your code more readable. Okay, when the type is obvious. So here the type is kind of obvious. We know hobby is a string, and hobby will also be a string. So yeah, and it will be what and if you overuse it, okay. So now this is like a Python, right? You don't have to remember and type any type. You can just say auto here and there. But there are static types. It will infer the type. But if you overuse it, if I put auto everywhere, then what will happen is it will make the code less readable. So you don't like when you're reading the code, you will not understand what type it is. So that's very dangerous. All right. So you have to you have the freedom to use it, but you have to use it wisely. Then namespaces are good. Okay, that's what I told. Right. Keep asking questions, please. All right. So next one is I'm going to show you debugging. All right. So I think a lot of people, we don't use debugger. So we usually use the print statements. Okay. So we keep printing stuff and to find what is wrong with the code. And that is not good. So you have like very good debuggers available, and especially for C++ and stuff. Okay. So let me demonstrate you. So like this code is just there for reference. Now this is the code I showed you here. Okay, so first I'm going to debug using VS Code. So I think like this is very lightweight. All of you can get this. You can just download VS Code, then go to the extensions and you install this. You type C++, and okay. So this is like the Microsoft C++ extension. Install this, and this will have like this. This comes with the debugger, and that's what we are going to use. And yeah. So if first thing is like I can put breakpoints in the code. Okay. So here and there. And what happens like when you put the breakpoint and I start debugging, it goes and the code will pause there. Will pause there, and then I can see the variables and I can do all those things. So I have put a breakpoint here, and then I will save the code and I Control Shift P and build debug file. Say this one. All right. So it goes and okay, it's somewhere here now. It's asking my part of the code. Okay. So all right. See, now it has hit the breakpoint. It has hit this breakpoint. So now I can open this debug window over here. All right. I can open the debug window and I can see stuff. So I can see the value of variables here. So this int variable, okay, its value is 26, and there is a variable called greeting, and let's see what the value is. The value is like WELCOME. All right. So yeah, and then you have another variable called name, and that has this one. Okay. So okay, and you can add the variables to the watch. Okay, and you can add expressions. So if you are here, I have added an expression where the age is less than 18, and if I just add here, so age is say greater than 10. Add it here, it will say true. Okay, so now the program has stopped in the middle, and now I can check all the values whether they are true or not. Okay, so this is call stack, whether like you have, if you are inside a function of a function of a function, then those will show up. All the different functions that are being called now will show up. Then you have like all the, you can remove the breakpoints dynamically. You can remove here and play. All right, so here you can go to the next step. So if you say step over, it goes to the next line. Okay, it goes line by line from that point. Okay, so similarly you can yeah, pause, and you can restart. You can do all those sort of things. And you say step into, if you have like a function, say if I have a function here, and I will say step into, it goes inside the function. Okay, and it goes inside the function step by step. All right, so like that. Okay, so you can do all those sort of things. You can go through your step by step. So rather than just saying print here, print there, like that, we do that all the time. So rather than that, you can use a debugger and debug your code very effectively. It's very helpful. All right, so now that is a debugger all of you can get, and so because it's kind of lightweight, and now this is a serious debugger. All right, so this is Microsoft Visual Studio, and I think this is the software. Yeah, so this is the one that is used professionally to build big applications, say Photoshop, that kind of things. So they use this one. So like, don't be afraid, like all these things won't show up when you open it. Let me show you. So yeah, so now this has the, let me take the same code and I will demonstrate it here. The basics. All right. Okay, so this is Visual Studio. Okay, Microsoft Visual Studio, and I'm going to start debugging. But before that, let me put okay, it's okay, it's fine. So let me put some breakpoint somewhere. Put one here, and yeah, maybe put one here. Right. Then start the debugger. Okay, so it runs the program here. It asks me my name. All right, and it has hit the breakpoint. Okay, you can see here. All right, now all these things you can get it this way. Just close it just for a moment. All right, so if you want to open these things, okay, from scratch, then you can, in the debug menu, you have stuff. Go to Windows, and if you say breakpoints, this window will come up. And all right, then you have the watch window, watch one. Okay, so this is the watch one. So I can take any, say age, if I want to see age, 26, and name 26. So it's the same thing, right? So like, then why do you need this? So why do we use this instead of this one, Visual Studio Code? So the reason is like this one. Now see, just go there, and if you take memory, All right, it will show you the contents of your RAM. So like in your computer memory, like what's going on, it will show you. So let me show you this. For example, I'm asking for the address of a variable, address of age. Okay, so the address of age is like this address, and I'm going to type that address here in the RAM. So 00 okay. All right. So 0066, sorry, 006 FFB74. All right. So if I go there, I can see the value is 26. Okay. So okay, when you go to this point, it might not be like this, and the reason might be over here we have like different options. So I can say 1 byte integer. So if I say that, now you have like different bytes. So this is the first byte, 2, 3, 4 bytes. So now we know the integer is like 4 bytes. Okay, I will show that in the following slide. So integer is a 4 byte. So this integer actually takes all this memory. All right, so this entire memory is taken by one integer. All right, so 4 bytes. And so that has the value 26. All right, so sometimes you might get this in a hexadecimal. You can change this one base to hexadecimal. So it might show up like this, or else like, yeah, so it might show up like this. Then you can just right click and say what signed integer, and then you can say a 4 byte integer. All right, and then you can see these things. Okay, so yeah, so you can hit the breakpoints and you can see the stuff, and you can, in here you can see the diagnostics. Okay, the process, like the memory taken by your process, the CPU, whether process going up or down. You can find the memory leaks here. If you have some memory leaks, it will go and blow up. So it has all the advanced features. Okay, and there's like one more thing. Okay, so you know about compilation. So I hope. So that means like we write the code in C++ and over here, and what we do is we compile. Okay, so C++ is a compiled language. Python is an interpreted language. Which means like when you finish writing a C++ program, you hit compile, and what will happen is like it will convert it into assembly, right? It will convert it into binary file, and that will be assembly. So what is assembly? Assembly is like the fundamental language for a particular processor architecture. So each processor architecture has a separate assembly language. Okay, so the computers we use, like the laptop I am using, and most all the computers that we are using, they have like x86 architecture. So x86 is Intel and AMD, so both are using that one. Then all the phones you have, they have ARM architecture. Okay, old Apple phones, they have different architecture, but they also ARM. Yeah. So yes, I think. All right. So like that, you have like different architectures. So here, when you compile and when you debug and stuff, you can compile in 2 different architectures. So over here, you can change the architecture. This x86 I'm compiling here. All right. And at the same time, like now, okay. So compiling means it will convert this into an assembly language for one particular architecture, right? So how do you see that? So you can see that you right click somewhere, say somewhere here, and I will go to disassembly, right? So if you open that, and here you can see the assembly code. All right. So these are the the ISA, we call the ISA of x86. Okay. And that's a compile code. All right. So now it is compiling, or it's running in the debug mode, which means like it is not doing any optimization. The compiler is not doing any optimization, and this code will be quite large, a bit large and stuff. But here you can click the down arrow. If I stop this, I can click the and go to release mode. And now if I compile, it will be very optimized. And sometimes you can see that some variables have disappeared. So if I am not using a variable, that variable will disappear, because like the compiler will optimize it. Okay. So why do we have 2 modes? Because the like compile optimization can introduce bugs. All right. So which is why we always do the debugging in the debug mode without any optimization to find our own bug. Then finally you turn to release mode, and then sometimes you might find 1 or 2 bugs which are created by the compiler. All right. Then you have to solve that also. All right. So those are just C++ things. Yeah. Okay. Then these are the different parts of the window. All right. So the next one. Okay. So data types. Okay. So you know about some data types. So these are the all different types. So like for each of these data types. Okay. So bool is whether it's 0 or 1, true or false, right? So that is like 1 byte. Okay, so you just need 1 bit, but bool is 1 byte because that is the smallest accessible memory. Like you can access only 1 byte properly. All right. So and where you can use it to have the true or false flags. All right. Then you have say char data type and int, short and long and everything. So they have like these different say int is 2 bytes in AVR in the microcontroller, but it is 4 bytes in a computer PC. Okay, and so on. So like if it is 4 bytes, then it can hold what are the numbers, maximum number and minimum number it can hold. Okay, so the general int is actually a signed integer. So when you say int, it's a short form for signed integer. So that means it can store from minus, say, so this is like you have 4 bytes, then about 32 bits, then you have 2 to the power 32 different values, right? So half of them are stored as like say negative values, and half of them can be used for the positive values when you use for signed. And when you use unsigned, you get a bigger range. So if you're only going to use positive numbers, and if you want a bigger range, you can just use unsigned int. Okay, like this. Like that, you have like different values. And for an example, you can see long. Okay, so long is actually this much. Okay, so that's 8 bytes. Okay, so long is 8 bytes. And with that, you can actually store the number of milliseconds that are there in 585 million years. Okay, so if you want to calculate, if you want to count, if you put a counter to count the milliseconds in a microprocessor, and you just leave it there, and if it somehow survives 585 million years, it won't. If it did, it will never overflow. All right, so it has that much value. You can store it in 8 bytes, long. All right, so float is like fractional numbers, and double is like more precise fractional numbers. Okay, so if you want to 3.14, 2.7, or those kind of things, you can store as float and double. Then pointers. So pointers are like we will look at them. They are memory locations, and it depends on the architecture. In the 64, in my computer, 64-bit architecture, so it has 8 bytes. Okay, and if it is in AVR, in Atmel chips, you have only 2 bytes. All right. So okay, so next one is data types and casting. So all right, so casting means you can take one data type and make it into another data type. Okay, that is cast. So the name comes from iron, like metal casting. You take something and you form it into something else, right? Okay, so okay, so while we look at this, we can see okay, so in terms of data types, you can see that if you try to count beyond the range in the data type, it will cause an overflow. All right, so for an example, I have saved here variable si. What is si? Si is an signed integer. Okay, and I have stored this very big number into it. All right, so this very big number, negative number, it is the minimum number. You can see, like I calculated from previously, and I have put that value here. Okay, so that is the biggest negative number you can put, and if I try to put that, it will work, and if I print it, I will get the correct answer. But if I subtract 1 from it, what happens is it overflows. Okay, it overflows and you get the positive number. So like you have that, those are called overflow errors. If you try to add or subtract something, and if it results in something bigger than the data type. So for an example, char is 255, If you try to add to that, it will become what a 0, unsigned char. So like that. All right. So okay. So then what happens, like the casting. Now casting can happen explicitly or implicitly. So implicit means like you are casting something, but like without your knowledge. All right. So that is implicit casting. So for an example, here I have created a variable which is unsigned long. So which is like and it holds a very large value, right? So what now I'm doing is I'm assigning that variable which holds this very large number. If I print it, it will work properly. I'm assigning that into var si. Var si is an integer, and integer can't hold that large value. All right, I'm assigning this. It will not show any error. That's a problem. What it will do is it will implicitly cast, and when it implicitly casts, you're going to lose data. Okay, and now if you print this value, it will be a smaller number than this one, and it'll be a completely different number. Okay, so these problems are quite dangerous, and you have to keep this in mind. Okay, so you don't get these kind of problems with say Python or anything else. Okay, even Python int, it will automatically resize. Okay, so you don't get those problems, but here, because you are working on the deeper level, right, in like but the very low level, just on top of hardware, you meet these problems. All right, so why is this important? Now for an example, like there has been accidents. So sometimes, like so I heard of what a spaceship crash. So like millions of dollars lost because of what the float value which they cast into this one, it overflowed. Okay, so it like those kind of errors, it can cause like massive damages. So we have to be very careful with these. All right, so then this is implicit cast. Another example of implicit cast, that is like if you are doing an operation, if you are multiplying two numbers together, if you're adding numbers together, and if one of the number is a float, pi f is a float, okay, 3.14 is a float, and this is a this is an integer. Okay, radius I is an integer, and if you add them together, what happens is like the integer becomes the integer becomes a float. All right, so integer gets automatically casted into a float because float is a more general data type, right? So that casting automatically happens. So this doesn't throw an error. So you get 2 into pi into r without any problem. 2 is an integer, this is an integer, this is a float, and the answer you will get as 62.8. There's no problem. And yes, then explicit cast. Explicit cast is done like this. You put a bracket of your data type inside, in front of it. Okay, you can cast it explicitly. And why do you use explicit cast? Sometimes the compiler is too dumb and it can't figure out like what you're trying to do. Okay, in that case, it's better to do that. And sometimes if you are doing something complicated and if you want to keep it readable, then you do it. Okay, and here, like why we do this, like for example, the one of the reasons where we really use explicit cast is like with pointers. Okay, so and we'll look at pointers in a moment, but the idea is like if you have a if you're programming on microcontrollers or NatMel chips or something, then all right, if you're programming on a computer, like a normal computer like this, then you don't randomly go and write into memory. Okay, so you can't just take a memory location and write into it. Why? Because the operating system, which is underneath it, it gives the ownership of the memory to different programs. Okay, so if you randomly take a memory location, it might be owned by some other program. All right, so you can't do that. And even the memory location owned by your program, you can't randomly take it. Why? Because like if you try to allocate some another variable, it might get allocated onto the same place and you will lose the data. Okay, so you don't do those kind of things. You just use like say float pi equals something, then it will automatically, it will take 4 bytes in the memory, and it will store this value over there and it will remember the location for you. So you don't do that. But however, when you are doing embedded programming, there are some ranges in the memory which you can access without any without these problems. Okay, so that those are like outside the the control of there are different data address ranges which are used for different purposes. So for an example, some registers. Okay, so registers, they are they are not used as variables by any program. Okay, so in that case, if you want to access a particular register, and if you have this address like this, so let's say this is the address of register, and you want to access that particular register, what you do is you can simply take the address, because you know the address from the data sheet. You take the address like this, so like 1111. Okay, then you cast it into something. Okay, because you say int, you cast it, and then you can write something into that. All right, so write some value into that. So like that you can use those kind of stuff. Okay, so that is why we need explicit casting. Right. So okay, then next one is okay, so before we go to the yeah, so before we go further on, I want to introduce classes. So usually classes are introduced at the end, but I'm going to introduce here. So the reason is now C++ is basically C with classes, right? So it's one of the most powerful features in C++, and you have you can do whatever you want with classes. Like you have all the OP features, right? So the first question is why do you want to use classes? Okay, so yeah, so the answer to that question, let's take a kind of practical example. So I don't want to take examples like say dog is a class and animal is a class. So I don't want to do those things. Let's take something a little bit practical. So that is okay, so if you are working with HBridge, okay, so HBridge is a motor control, right? So if you what is the purpose of that? So the purpose of that is if you want to change the direction of motor, okay, as you want. So while it's working, you want to suddenly change the direction of motor, and you want to stop and change and those kind of stuff, then we use an HBridge. So this is ideal for robotics projects. So if you are making a small robot, almost definitely you'll be using an HBridge to control the wheels. Okay, so how does an HBridge work? So we don't have to go into the circuit, so that's not the scope. But the idea is there are two pins, and in the HBridge driver, for each motor there will be 3 pins. All right, so pin 1, pin 2, and PWM pin. All right, so pin 1, pin 2, and PWM, you will have 3 pins for each motor. What happens is this pin 1 and pin 2, they determine the direction of the motor. Okay, so if you keep pin 1 high, all right, or else if you close pin 1 like this is pin 1, that is pin 1, both are pin 1. If you close pin 1 like this, and if you open pin 2, the current will flow in one direction, and motor will rotate in this way. And if you open pin 1, and if you close pin 2, if you give a voltage to pin 2, and if you remove the voltage from pin 1, what happens is the motor rotates the other way. So like that you can make the motor rotate any way you want by changing the values in pin 1 and pin 2, right? So yeah, and then by changing the value in PWM, so that's an analog value, and so that's an analog output pin. By changing that, you can make the motor go faster and slower and stuff, right? So that's the simplest explanation. Right, now what is the problem? So the problem is each motor needs 3 pins. So to control one motor, you have to control 3 pins, right? So now here I have written a very simple Arduino code. So this is the kind of code we wrote when I first started using Arduino. Okay, so yeah, so what you do is I have 2 motors, right motor and left motor, and now I tell, okay, right motor's pin 1 is 3, pin 4 is the pin 2, pin PWM is 5, then left motor pin 1 is 8, pin 2 is 9, this one is 10. So like that I assign separately, and then I put the pin mode, so all of them output. And inside the loop, so inside loop, what I do is if I want the motor to go forward, okay, then I make one pin high and the other pin low, okay, and then I do analog write to the PWM pin. I write the analog write again, here I am doing a serial also. All right, so there's a tiny mistake. All right, I have to mention serial begin. Okay, so I do a serial write. Now, when I do that, okay, I do the serial write. So like that, if I want the motor to go reverse, I have to write all these 4 lines and forward 4 lines, this one. So I have to do this throughout the code. Now, if I am writing a very big program to like a pretty complicated robot, say it has to go and do a task, like in a robotics competition, you have to do like a lot of tasks. So then you have to move left and right and forward and backward, and you have to do all these things. So do that, I have to write these lines again and again and again. So one problem is writing. Second problem is debugging. Okay, so it is very hard to debug this one. Now see, now I have no idea whether pin 1 high and pin 2 lower, forward or backward. Okay, the only way to figure that out is by testing it. So you run something, you like put it one way and test it, and then you put it the other way and test it. Okay, and then like if it goes forward, then you pick that one. Now, if I make a mistake somewhere here, okay, in here, like if I change it the other way or something, then suddenly the robot will start going in a very wrong way, and it might crash also. All right, and it's very difficult to find those kind of bugs. Why? Because like I'm writing the same code again and again, and I can't find where the bug is. Okay, there's too many things, I can't find the bug. So all these are like it's a very bad code. All right, so it's not a good code. Then in that case, how can you simplify this? Okay, so what we do is, okay, code repetition is error prone. We write it as a class. Okay, so now this code is bigger than that code, right? It might look bigger than that code, but then it is more simple. All right, let's see how. Okay, so the way that is simple is, okay, so this is your class. All right, so what is a class? A class is a user defined type. So it means you have data types, right? You have int, you have string, you don't have yeah. So even string is a class actually. So you have what int, and you have say char, and those are like primitive data types. Okay, so like that you can define your own type, own data type. Like that's a class. Okay, so here I'm defining a type that is motor. Okay, and the idea is like you write your class only once, and you debug it only once. You make sure like your class is working and everything, and like you debug all the functions and everything. And after that, you can use that class to create any number of objects. And you can control the objects without worrying too much, because you have tested the class very thoroughly. All right, so that's the idea. So here what I'm going to do is I'm going to write I have written a class for motor control, and that is for the edge bridge motor. So you can see one motor in the edge bridge has what? 3 pins, pin 1, pin 2, and PWM, the 3 pins. And I'm going to keep these 2 kind of variables to remember what's going on. The speed and is forward. Okay. Yeah. So to remember stuff, I'm going to put this. Then all right. So what is this? Okay. So all right. So before that, let's see. Okay. So this is a class. You define a class like that. And how do you use a class? This is how you use a class. Okay. You say motor write equals motor. This write is basically the name of the motor, and 5 is the pin 1, 6 is pin 2, 7 is pin 3. And now I have created a new motor. I have created a motor object. And then how do I use it? I use the motor like this. I can just say motor write dot forward 50. And when you say that, the write motor will go forward by 50. And I have already debugged the function, the forward function, so there's no problem. Then reverse and forward and reverse, I can do that. All right. So now you can see the main loop has simplified a lot. So this is our actual program, right? The loop. So everything else, so this is just, you can keep in a separate file. So the main loop is now very simple. All right, simplified a lot. Now let's see inside here. Okay, now let's see how to define a class. And when you define a class, you can see there are what attributes. Attributes means like the member objects, like member attributes. So these are, can be 2 types of attributes. Some are private and some are public. So anything you can put under this private will be accessible from using the functions inside the motor class only. Okay, so that means only these forward and reverse functions can access these private variables. So that's quite good. And then like this public is like anyone can access it. That means you can access it from outside. All right. All right. So okay. So here we have the first one. This called the constructor. The motor is a constructor. So constructor means it actually creates this object, whatever the object you are trying to do, and gives you. Okay. So it has the same name as the class. So that is the convention. Same name as the class, and it can take a bunch of values inside. So what are the values? Pin 1, pin 2, pin PWM, and the name. It takes them inside. So now the next one is this one. This is called the initializer list. Okay. So what does that mean? That means I can initiate the values in this class. So pin 1, pin 2, pin PWM, and speed, all these things. Yeah. So one is asking like, do we have to mention it explicitly whether they are private? So it's better if you mention them explicitly. I think they are private by default, but it's better to mention explicitly because like it makes the code more readable. Okay. So when you look at the code, you know, like this is private. All right. So keep the code readable. All right. So, okay, you can do that. All right. So you can do that. And then what you can do is, all right. So this is a constructor and it's a function that creates the object, and you have, and you can do some initialization. So now you can see that pin mode output, I'm actually doing it here. That is inside the constructor itself. So I'm not doing it outside. So even that is handled. All right. So I don't have to write it again and again. Okay. So I'm doing that over here. And then next one, what happens is like, okay. So the forward function. All right. Okay. So this is initialize a list. And this initialize a list, basically what it takes this name. This name is this name and assigns that to the class name. All right. So this now this name and that name are different. All right. So this is actually the argument. Okay, argument of a function that is the member attribute of the class. All right, those are two different variables. So by doing this name, what I'm doing is I'm taking the argument and I'm assigning that to that one. So it is okay. It's a good practice to name it similarly if they have the same purpose. Okay, so if you try to put different names here and there, then what happens is like you'll get confused. So keep it readable. All right. So okay. So the next one, this is a member function. Okay. So the constructor is also a function. And now this is also a member function, and these are public, right? So constructor has to be public, and these functions are also public. So what happens is like when I say forward, and when I give a speed over here, you can see forward 50. I want the motor to go forward. Okay. So with the speed 50. All right. So what I do is like I do digital write and what pin 1 high, pin 2 low, and I give the what PWM. Okay. So to the PWM I give the speed, and then here I am doing the what I am doing a serial print element. You can just remove these things if you want. All right. Then okay. Then what is this? So this one is I'm taking this in speed and I'm saving that in the class variable. Okay. So now the problem is like this class variable is their speed. Now this also speed, but they have the same name. Okay. So then it's kind of ambiguous, right? Like how do you access one particular thing? Okay. Now this and that can be and will be different. Okay. So this is something you give from outside. Now that speed is something that's inside the class. So how do you differentiate between them? For that you use the pointer. All right. So special pointer. This is a special pointer. So that points to that particular object, current object. Okay. So when you say this speed, then you get the speed of the object itself. Okay, and you are assigning to that, you are assigning the argument in here. All right, and similarly this dot is forward true, and it has no ambiguity. Now this is forward is, there's no ambiguity. In that case, you can just remove this. So like you can just say is forward equals true, and it will know that you're accessing that value. Okay, so this is something like self in Python. Okay, but in Python you can't get rid of it, right? So you always have to say self dot, and I think half the code will be self. So here you don't have to do that. So you can just remove you can omit this whenever you want. Okay, and it will still work if there's no ambiguity. Okay, so all right, so this is the member function, and okay, so what we can do is these member functions, we can declare them. So we have to always declare them inside the scope, but you can define them outside if you want. Okay, so here I have declared and defined one function inside, and I have defined another function outside, just to show you so how it's done. So this is reverse is like anyway they had to be declared inside, but now I'm going to define it outside. So this is the definition. Okay, so I have defined it outside, and all right. So all right, so that is the whole idea, and serial begin, and we run it. So this is an Arduino code. It won't run in VS Code. It runs in Arduino. All right. So okay. So this way, very quickly, you can create a library, a class for your motor, and you can use it. Okay. So what you do here is like, okay. So now this, if you, okay. So now I have taken like a stripped down version of this one. I have removed some functions, and to show you how classes are represented in the memory. All right. So yeah, I'll show you later also, but like here for the sake of completeness, I will show you here. Now let you see, when I create a function like that of this class, P1, P2, PWM, I'm creating 10, 11, 12, right? And I'm putting the value to P1, to P2, and PWM. So that's like a different class, right? So when I do that, I'm creating a member M, okay? So a motor M, and that's the object. And I'm getting the address of the object. And when I look at the address in the memory, I see that you have 10, you have 11, and you have 12. And they are incremented by 4 bytes. So what does that mean? That means this has only 3. So from here you can see only 3 values, right? So only 3 attributes, and each of them are 4 bytes. So the whole object is actually just 12 bytes. So 3 into 4 is 12, right? So there is no overhead. So like there is no even like any kind of indication that this is a motor object or something. Also, so that's like 0 overhead. So that is the one huge advantage of C++. All right. So the object-oriented stuff and all the advanced features are there, but without any overhead. It's very compact. But in Python, if you take, for an example, a bool variable is, I think, 24 bytes. Okay. Something like that. So like most of the variables are like 20, 30 bytes. Okay. Even if you are storing like 1 byte, the whole object will be like 20, 30 bytes. Why? Because it has to store a bunch of other things. All right. So in C, like it is very stripped down. So you have like what, extremely optimized. That's what I want to show here. All right. Now the next one. Now you have made say you have made a motor class, the same motor class. Okay, it's not new code. It's the same code from the previous one. All right. So that code, you want to make it into a library. Okay. So how do you do it? Okay. So now this might seem familiar. Now just look at this main file. Okay, after you create the library, you will be using this main file. Okay, so this main file you are doing include motor.h, and afterwards you are saying motor left equals this, and motor right equals that. You are creating 2 motors, and you are saying motor forward and motor reverse. Your main file is so small. Look at this. You have only this much. You have only this much compared to all the code you wrote here. Okay, so instead of writing this much, your main function will be very small in here, and it's very easy to read and very easy to debug also. All right. So now can you see the pattern, or like what's happening here? That is, now if you have used Arduino, if you use Arduino, of course, like in the Arduino libraries you used, the LCD library. Okay, so all the all different kinds of libraries you use, Sonar library. Okay, all of them, are actually made this way. Okay, so the people who built the Sona module, okay, or like the open source, what the community, what they have done is they have created this kind of files, CPP file and H file and everything, and they have given you and those things, and they have created classes. So all the Sona module is created as a class actually. Okay, so just like I created the motor as a class here. So the Sona module is created as a class, like that LCD is created as a class, and all of them are created as classes. And using the class, you are making a Sona object. Okay, in when you are using Arduino, that's what you do. You create a Sona object, and then you like check whether the object is in a certain distance or get the distance. You do all those things, right? So yeah, so this is how those libraries are written. All right. So right. So now let's see how to write the library. Okay. So it's the same code. There's no difference in the code. I have just rearranged stuff. Okay. So thing is like a library usually consists of two files. So one is the H file and the CPP file. Okay. Or this can be CC file or INO file or whatever. All right. So this H file is called the header, and the header contains only declarations. Okay. So what are declarations? By looking at this one, you can see it's the same code, but I have moved the stuff. So you can see I have declared the function forward and reverse. I have just given the signature. I have just given the function signature. Even the constructor, I have given the function signature only. Motor, string, int, and this is void, int. Okay. So I have not written any code here. Okay. So that is the standard way of writing header files. We don't, it's a convention. You can, but we don't put code inside the what actual code, the code that does work. You don't put that into header files. All right. So in header files, we keep only definitions and only declarations. Okay. So only class declarations, function declarations, we do keep there. All right, like this. Then okay, now let's look at this. So this is something common you see everywhere, like things like hash, if and def, and hash define. So once again, all the hashes are preprocessor directives. So that means like what when you click compile, the first thing that runs through your code is a preprocessor. It will do certain things for you. This include we saw before. You just copy paste code. All right. So instead of that, okay. So here you have okay. So this the header guard means okay. So header guard has a purpose. So what is the purpose? Now sometimes when you're including files like this, I told you that preprocessor is quite dumb. It will just copy and paste files here and there, right? So it will copy the code from the Arduino H file and Motor H file and paste it here. So while you do that, you include a couple of files here, and then if you include the same file here again. Okay, now see, I have done that, right? Now here I am including the Motor H file. This is Motor H. Okay, and inside Motor H, I'm including what? Arduino H. Okay, so this Arduino header file will have some code. So if I do that, if I do this, what will happen? The Arduino code will get copied. Arduino H code will get copied and pasted into this file, and then this whole file will get copied and pasted into this file. All right, and then again Arduino H file will be copied and pasted into this file because the preprocessor is dumb. Okay, so when you do that, what happens? Now you have like multiple copies of the same classes and stuff. So the stuff inside Arduino H will get copy pasted multiple times. So then C++ will throw an error and it will tell you, okay, you have like the same class twice and you have no idea where. Okay, so that's a big problem. Like with preprocessor, it's very difficult to find the errors. Okay, so it is quite dumb and it will not tell you where the error is, and you have to like spend some time to figure it out. Okay, so how do you solve that problem? Now to solve this problem, what we do is we include header guards. So every time when you add the header file like this, okay, you add the header guard. So the header guard is this one. So this is the old way of writing a header guard, and this is the new way of writing a header guard. All right. So old way I have commented it. So it says like if and def motor H. okay, and you put the like a big if. So this is like a big if condition, and that if condition is for the preprocessor, not for the compiler. All right. So that means motor H is like a name. It's like a name, and if you define it, okay, if it is already defined, then this code will not be read by the preprocessor. If it is not defined, this code will be read. So which means like the first time preprocessor reads this, it will define motor H and it will read this code. The second time the preprocessor read this, it will not go through this one because like motor H has been already defined. So that's what you call a header guard, all right, to prevent this code being included multiple times. All right. So now that is an old practice, and so the new way of doing that is like you just say pragma once. Okay, so the old one also will work, but if you just say pragma once, it's easy to type, and when you read you understand. So pragma once means you include this file only once. There's a meaning of it. All right, so that's very simple, and this is declarations. There's no definition, and over here you have the actual definitions. Now can you see? All right, so this is the constructor. Okay, it's the constructor. Motor, that's a constructor, and so motor forward, motor reverse. Okay, so and the double one, that's called the scope resolution operator. So that means from outside you can access this scope, the class scope. All right, so that's how we do this, and we write the same code here we got from previously. Now this is the CPP file, okay, or else CC file, or else like INO file. That is a file that contains all your actual code, whether all the functions and stuff separately. So what happens is like your compiler will actually compile this. Okay, will compile the CPP file separately. The CPP file will be compiled and separately, and then they will be linked together by the linker. All right, so that's how the library is actually working. So all right, okay, so you have the this is the main file. Okay, what is the purpose of is forward? Okay, there is no purpose. Okay, so I just put there like to store the value of what is forward, and like I can write another function to get the value of it. Okay, so while the motor is running, I can ask whether the motor is running forward or not. Okay, so that is the purpose of is forward, and you can just remove it. All right, so I just want to show what different what member variables and stuff. Okay. All right. So now this CPP and this CPP and H files, the library, you will build the library, you will test the library very thoroughly, and that's how they release to the internet. Like, so all the libraries you download from all the Arduino libraries you download, those have been tested and everything. And now because they have tested it, you don't have to test it. You just simply include, and then you write your code. Okay. So like this, like for an example, if you are making robots and if you are going to a lot of competitions, you can gradually build your own library step by step. Okay, so let's see the time. 11:15. I need to finish by 12, and I think I can. Okay. All right. So okay. So now what pointers and memory. Okay, so this is the fundamental, very key concept of what C++, OC, both together. All right. So now, if you want to understand something very deeply, very thoroughly, then make sure you understand this properly. And if you have any questions, ask me. All right, keep asking me. Okay. So the idea, like, so I told you before. So C++ gives you very fine control. Okay, which is why we use C++. All right, you can control the memory and everything very, very finely. All right. Okay. So how do you do that? So you do that because you are able to access the memory wherever you want. So whatever the value like in the memory, you can write there, you can read from there, you can do all the stuff you want. All right. So that is like the biggest advantage in C or C++. All right, the pointers. And that is also very quite difficult to understand, and sometimes like quite difficult to use and to debug also. But still, like it is the most important feature in C++. All right, so let's see what we do here. See if you can understand this. So this is the data memory. Okay, so like the program memory and data memory, so they are together, they are the same in a computer, and in some microcontrollers they are separate. All right, so it's the same memory. So what is a memory? Memory is the DDR RAM. All right, so the RAM you have, that is RAM, another word is memory. All right, so now how do you visualize this? So what is memory? So if you ask what is memory, it is basically an array of locations. Okay, so each location is like 1 byte. Okay, so it's like an array of locations, and each location has an address. Okay, so okay, so which means like now if my RAM is like 16 GB RAM, then there are 16 billion basically what locations in there, bytes. Each location is 1 byte. There are 16 billion, over 16 billion locations, right? So each location has an address. Okay, so all of them, they have an address. So then what happens? Okay, so how can you visualize it? You can visualize it like this. So let's say from the bottom it goes up. Okay, so the bottom you have 0, 1, 2, 3, 4, like that. You have all the addresses up to like the maximum address you have in your memory. That's a RAM. All right, now let's see, let's go through this code. All right, so here I'm going to show you a bunch of different pointers, bunch of different variables and their pointers. So for an example, I'm going to show you an int pointer. Then I'm going to show you a pointer to a custom object, custom class, and a pointer to a function pointers. So let's see. Let's start with the int, the very simple one, which we understand. Okay. So here one thing is like, okay, this, all right. So, okay. So what you do is like, let's, if you go into the main function, the first one is we say int I equals 100. Okay. So when you say that, what happens, you know, you are declaring and you are initializing. You are declaring means it allocates some part in the memory for you. That is declaration. When you say int I, okay, it keeps a separate part in the memory for you and it names I. So this is named I. Okay. And when you say int I equals 100, what happens is the 100 gets put into that. Okay. So this 100 comes into somewhere in the memory. Now, what is the address of the location? Let's say the address is this one. Okay. So why do we have it in hexadecimal? Because like otherwise it will be very hard to read, because there are 16 billion numbers. Okay, so the full number will be something like that. It will be a very long number. Okay, so if you write in hexadecimal, the number will be more readable. All right, it's the same number, but it will be more readable. All right, so because of that, we write the addresses in hex notation. Okay, so now let's say this, when you say int I equals 100 to some location, it will allocate to some location and it will put this 100 in there. Okay, so now, yeah, you can clearly understand this I actually means 100 and the address is this one. Okay, now similarly, if I create a motor object, okay, so motor object, and I showed you before in the debugger, if you create a motor object, what happens is like it creates, yeah, so it creates the object somewhere in the, again in the memory, and when you say motor M, it allocates 12 bytes. Okay, 3 ints, P1, P2, P3, 3 ints, so 12 bytes it allocates, and then it will when you say like this, when you call the constructor, here you're calling the constructor, when you do that, it will create the object for you and it will assign the values there. So 10 goes to P1, 11 goes to P2, 12 goes to PWM, 10, 11, 12 to this location. Okay, so if you say m.p1, you get this value, m.p2, this you get this value, sorry, this should be PWM. If you say m.pwm, you get this value. All right, so you get all 3 values. Okay, so now you can see all are there, like I showed you before also. So like all are together. So like 0, and this is 4, and this is 8. So which means like 4 bytes, 4 bytes. And that is why I have marked this in different sizes, the boxes. Okay, so these boxes are 1 byte each, and these little bit big boxes are like 4 bytes each. So this is 4 byte because that's an int. Okay, this is a 4 byte. But in actual memory, like all of them are like 1 byte each. Okay, 1 byte each. But then like we take 4 4 bytes together as one block, and we call that an int. Okay, right. So like that, we take 12 bytes together and we put a motor object there in here, right? So similarly, now I have put a function here. Okay, this function, I write it somewhere over here, and when the code compiles, okay, when the code compiles, what happens is like you get assembly, right? So the assembly value, it is stored in some in the program memory. Okay, in computer it will be the same memory, like in this chip it might be a separate memory. So there it will be stored to a particular place, and the assembly values will be stored. Okay, and to that you have that also will have an address to some location. Now what I'm going to do next is, okay, now look carefully, I'm going to take the address of different variable. Okay, so this at is the address of operator. Okay, so when I take at, okay, when I take at, what I'm doing is I'm taking the address of this. So if I ask for I is 100, m.p1 is 10, m.p2 is 11, m.pwm is 12. Okay, but if I say at I, it means the address of I. Okay, what is the address of I? Address of I is this hexadecimal 61FCDF. Okay, so address of m.p1 is this one, and address of m is also this one because they are same. Okay, like it starts from there, right? So the address of the object and the first member, like it's same because they start from there, and p2 and pwm. All right, so these are the address values. So if I want the address of any of these variables, I can just put at and get the address. All right, now after getting the address, what I'm going to do is I'm going to save that address in a variable. Okay, so the address gets saved inside another variable. I'm going to do that. What is that? So that is a pointer variable. Okay, so I'm declaring a pointer here. I'm declaring an int pointer. Okay, so this is an int pointer and write it as IPTR. Okay, so this int pointer, I'm declaring it here, and so that is this variable. All right, so when I say that, what happens? It will automatically allocate some location. Okay, how many bytes? So that depends on your architecture. All right, so if my one is a 64-bit architecture, then you will have like 8 bytes. If it's a 32-bit, then you have 4 bytes. Okay, so then that depends on the architecture. So that way, so like there is a size of address. Okay, how much? What is the size of address? All right, so it will create a variable in here. Okay, and that variable will be a pointer variable. This is a pointer IPTR, the pointer variable, and this pointer variable, see, it holds this value of at I. Okay, that's what I'm doing here, right? IPTR is equal to at I. Okay, I'm taking the address of I and I'm saving it in the PTR. Okay, now you can see IPTR, this 61, the value inside here, that value is same as this address. Okay, the address of I, this address is saved here. Okay, so similarly, the address of M is saved here. 61 FD00 is saved here. Okay, so that's a variable, but that variable holds the address of something else. Okay, now this variable itself has an address. That is something else. That's a different story. Okay, each variable has an address. So this variable also has an address over here, right? Okay, but okay. So similarly, I create a function pointer. Okay, now this is the function pointer syntax. All right. So function pointer, I'm saying int because this function returns an int. Okay, int, and so the star FPR means like it's a pointer to the function, and the argument is a float. Okay, argument is a float, and I'm getting the address of the function, and I'm saving there. It's a function pointer. All right. So then what I can do is I'm printing the different values, and I can see the outputs. Okay. Now this is how you access a member of an object. Okay, the member attribute. So if your member is okay, so M, what is M? M is a motor object. Okay, that object's P1 value, I can simply get it as M.P1. M.P1. Okay, so that is, I will get this value. All right, but over here the same value I also can access it as mptr this operator p1. Okay, so that means mptr, it goes there, and what is the object pointed by mptr? That is m, this one. This one's p1 is 10. Okay, so this both will give you the same answer, 10. All right, so there are, if you are accessing it from the object, you say m.ptr. If you're accessing it through the pointer, you say mptr this operator and you say p1. All right, so similarly, okay, so here I can just print the pointers. If you print the pointers, you will get the actual addresses. Okay, okay, and you can see fptr, and I can print those values. And okay, so here's something fancy. Okay, so this is basically what I'm doing here is okay, at the same time, now if I want to get the value, okay, so iptr, so now I have iptr, and if I just print iptr, I will get this address, right? Now I want to know the value pointed by this address. So that means I want to go there, this is a df, that is this one, and I want to get this 100. How do you get that? To get that, you say star iptr, that's a dereference operator. Okay, that way you can get the value back. You can, from here you can go here and get the value back. So that's a dereference operator. All right, star. So here there is like a small fancy example where like you can create a pointer to a pointer. All right, so that's what I have done here. So IPP, okay, this IPP over here, IPP is a pointer to a pointer. Okay, so what does that mean? So it is an address. It's a pointer, which means it's an address, but it holds the value of what? Okay, it says 61ff25. 61ff25 is an address, and if you go to that address, you get another pointer. Okay, so and if you go to that address, you get what? df, this address, you get 100. So this is a pointer to a pointer to a pointer. Okay, so it's a pointer to a pointer to an int. Sorry, it's a pointer to a pointer to an int. Okay, pointer to a pointer to an int. So that's why you have like two stars. Okay, so a pointer to int. All right, so and you do that by getting the address of iptr. Iptr is a variable, it's a pointer variable. All right, and you get the address of that. Okay, and if you want to get the values of those, you can see if you just print iptr, you will get what? IPP. If you just print IPP, you will get this value, 61ff25. If you dereference it once, if you say star IPP, you are dereferencing it, which means it goes to this address and it will print this value. Okay, you will get 61FC. If you dereference it twice, you are going to get what? You are going to get 100 I. Okay, so that is how the dereferencing works. All right. Okay, so yes, so let's see if you have any questions. All right, so yeah, see whether you understand it. So let me like run it in the debugger and show you a quick demo. Okay, so let me show the last one. So that is like I'll just say IPP. I get the value of IPP. Okay, so IPP is a pointer to a pointer to an int, right? So IPP is what? IPP is this one, 000 AFF 948. Okay, let's go to that place. AFF 948. 8. So the value held by IPP is that one. So if I go there, I get something weird. Okay, so this is like a big number. So it must be a pointer. So I'm going to say 8 byte and hex. Okay, so yeah, if I dereference it once, star IPP. Okay, so I see that, yes. So this is okay. Yeah. So all right. So this is run in 32-bit mode, I think. Okay, so that's why I'm getting the 4 byte addresses. All right. So this is 00 AFF. Okay, I see this one here. Okay. So if I go to that location, that means if I go to the location pointed by here 948, I get 968. This one. And if I go to the location pointed by that, let's see what I get. Get something like this. I get say 64. Okay, so that's in hexadecimal. And if I convert that to signed, I get 100. Okay, so I get an integer like that. So it's a pointer to an integer. All right. So that's how this works. And so the next one is like okay. So if that is understandable, then next one is point arithmetic. So this is an array of 5. It's an array of 5 numbers. Okay. So 5 ints. So 4 that's like 20 bytes in a computer, right? So you have okay, and that will get written somewhere. Okay. So array, then what will in somewhere in the memory the 5 values will be put 20, 21, 23, 24, 23, 24. Okay, 5 values will be put, and they in consecutive locations. So the arrays are stored like that. Okay, so next one, if you take the size of array, they remember the size. Okay, in C++, the arrays actually remember their size, so you will get 20. Okay, but when you pass the array into a function, if you try to do that, they will they will be casted into a pointer. So they will forget the size if you do that. Other than that, they remember their sizes. And all right. So here you can address. Okay, so I'm running a for loop, and I'm running a loop through each of these element. Okay, first element, second element, third element, and each element I'm taking the address. Okay, and I'm printing the address. Then then what I'm doing is I'm taking the array, so array pointer, and I'm adding 0, adding 1, adding 2 to that also. Okay, and when I do that, yeah, okay, so yes, and I'm taking the value also from there. All right, so when you do that, what happens is you can see that if you add the array plus 4, it points to this location, plus 8, this points to this location, plus 12, plus 16. Okay, so if you say what okay, so this should be 1, 2, 3, 4, right? So that's a mistake. Okay, so all right, so if you add yeah, if you add 1, 2, and 3, and 4, all right, so I will fix this before I upload. So this will be different. But okay, when you add 2, what happens is 2 times 4 bytes get added. Okay, so that's a pointer arithmetic. So when you're adding a number to a pointer, it shifts by the data type size. It goes to the next value. All right, so that way you have like a 2D array also. And I think I had to fix that too. But if you have a 2D array, then you can access things that way. All right. So you have, if you have a 2D array of this 1.1 and 2.2, 3.3. Okay. So yeah, if you have a 2D array of that, then okay, there's a mistake here too. I'll fix that too. All right. So I will fix that before the end of the next session. All right. Okay. So that way you have you can access then like 2D arrays are also stored consecutively. So first 1.1, then 2.2, 3.3, 4.4, 5.5, and 6.6 are stored consecutively. And by adding appropriately. Values are appropriately, you can add them. But you can't just add those subtract to an array. You have to cast it into a normal pointer, into a double pointer. Okay, so this is double, so that is like 8 bytes in size. Okay, not 4 bytes. All right. So next one is like local versus global code. So I think you know this already. So what happens is like you have yes. So you can store like if you define a variable outside all the functions, the main functions and everything, we say that's a global variable. All right. And so that's called a file scope or else a namespace scope. So what does that mean? That means like it can be accessed by any function in the file. It can be accessed by any this one in the file. So when you say local variable, you inside it in declare it inside a particular function or particular scope. Say in a for loop, inside the for loop, you say something like this, int var4. Okay, and if you say something and if you print that, what happens is you will get this yeah, you get that particular value, say 12. But you can't access this variable, this var4, this variable, you can't access it from outside. If you uncomment this line, I will upload the code. If you uncomment this line, you will get error. Okay, that will be a bug because like that's a local variable. You are trying to access it outside this braces. So you have to always access inside the braces. All right. So it's a very good idea to use local variables. Okay, if you are only going to use this inside this brace, it is better to put it here. Okay, because it makes the code very readable and it avoids some bugs also. All right, if you put it outside, then you might change it accidentally. So it's better to put it inside and it's very readable. Like you know that it's going to be used only inside. Okay, so always put the variables in the right scope. Don't put everything in the global variable. Okay, that's a bad practice, putting everything in global. All right. So that way, now this from inside this for loop, you can actually access this one as well as you can access the var function. So this is local to here. Why? Because this is inside that scope, right? Okay, this braces between that scope, you're accessing it. So it's fine. You can access the global variable as well, no problem. So similarly, you have you can access functions. Yeah, so like the variables inside functions, you can access it because it's in the same scope, global variable. And here, if you're accessing from a different function, the only thing you can access is a var_g, that one. All right, the global variable. You can't access anything else. So that's basically the scope. Then, so the scope says like where you can access and where you can't. All right, so that's the idea. Then there's something called the lifetime of a variable. So that means like when are the variables created and when are they destroyed. Okay, so you can create lifetimes. Okay, so the lifetime of a particular variable can be automatic or static. You can allocate it automatic or static. So whatever we normally do is automatic. When you say int var_g or something, it is automatic allocation. Okay, so what means the lifetime is limited to the scope. Okay, so for an example, inside the function, I'm doing var a1. It's automatic variable. Okay, so that's a normal thing I do. So if I do that, what happens when you when I call the function from here, when you go inside the function, you run, and when you exit the function, that variable is destroyed and it's freed. Okay, it's not used anymore. Okay, so which means if I here I'm trying to add the function increment a1 here. So if I do that, what happens is like I will use the scope. Say that's a question. All right, there's a noise from my microphone. Hold on. Yeah. So is it okay now?
Yeah, it's okay.
All right. So okay, fine. Okay, so right, so let me show the lifetime in this one. Okay, so as you see, like I'm incrementing the variables. Okay, I'm incrementing the global variable. I'm incrementing the global variable. I'm incrementing a1, and I'm incrementing the static variable also. Okay, in here. So if I declare something static, what happens is all the static variables, this one and this one, they get declared the first time I run the code. Or else during the compile time, when the code compiles, and when the program starts, actually not compiled, when the program starts, so they get declared. Even the one that are inside a function, they get allocated when the program starts. And then as you run the program, what happens is the value in them, what if it changes, it will remember the change. Okay, so it's var s1. Okay, I'm incrementing it here inside, and every time I'm leaving the function, okay, you can see the value is incrementing. Okay, so when I go back to the function, when I call the function again, it remembers the value. It remembers it's 12 and it's incrementing 13, 14, 15, 16, it's incrementing. But I'm doing the same thing to a1. It's an automatic variable, and a1 is not incrementing. You can see it's 10, 10, 10, 10. It doesn't change. All right. So yeah, it's the same case with this one, with the for loop also. Okay, a2 is not incrementing, but s2 is incrementing. So why does that happen? So why does that happen? It happens because yeah, because the static, they have a lifetime, but throughout the program. And now that is also a good thing. So that is if you want to something like that. So if you want this function to remember something when you call again, all right, don't use global variables. All right, if you use global variables, it is kind of like it's not readable also. All right, so better to put all the variables inside the function and make it static. So when you see the function, when you read the function, you know the variable is there. All right, and if it is static, you know that it remembers. All right, so that's the best way of doing it. All right, so okay, then all right, so I will quickly go through the rest. So this is dynamic allocation. So all we saw now are compile time allocation. It's automatic and static and everything. Whatever done is like you run the code, it will create it in the compile time. But now if you want to create an object based on, say, dynamically. So for an example, if you are going to take down say my hobbies or something, list of hobbies. Previously I had an example where I take 3 hobbies, but instead of that you want to take any number of hobbies from me in a command line. So in that way, what happens is like you can't do that with a normal way, because you don't know how many hobbies I'm going to give, right? So to solve that kind of a problem, what you can have is you can have dynamic allocation. Okay, dynamic means like in the runtime the objects are created. Okay, so we call it stack versus heap generally. So this is the way you generally do the compile time allocation, motor m, which we did before, and this is how you do a runtime allocation. Okay, so you create a pointer. Okay, motor like mp1 is a pointer, and then you say new motor. Okay, and it will create a new motor and like a motor object, and it will assign there. So this is runtime. So it doesn't matter how many times you call it, and you don't it doesn't have to know it advance. Okay, but whenever you do that, and here I'm doing that in a for loop also. Okay, so in a for loop I'm creating and adding values, okay, into an array. All right, so you can do that, but you have to remember that whenever you create something with new, you have to delete it. If you don't delete it, when the program ends, or when this one ends, the memory value, when a particular function ends, the memory will be still used. All right, so that is what you have to always free. Whatever you create, you have to always free, and always you have to delete. In C++, C you say free. Here also you have free, but we don't use it. We use delete. We have to do that. All right, else it will cause memory leak. So that's like a major problem. All right, the programs will crash when you keep on creating objects, but you don't delete them. Okay, they will stay in the memory, and like the program will crash. Yeah, those kind of problems. All right, but what now all this time we talked about pointers and like about new and everything. But the thing is, like, you don't have to use them most of the time. Okay. So actually, you can actually survive without new or without pointers. All right. How? There's something called smart pointers. Okay. So smart pointer is something like this. But okay, there are two types of smart pointers. One is a shared pointer, other one is a unique pointer. So what is the idea? The idea is like in Python and Java and everything. So they have something called garbage collection. Okay. So what is garbage collection? You don't have to worry about deleting an object. That's the idea. All right. So you don't have to worry about deleting. You just keep on creating objects here and there, and you just leave them. All right. So that's garbage. So after a certain point, like you create an object, and when you exit a certain function, if you don't delete an object, what happens? The pointer goes out of scope, right? The pointer to an object that goes out of scope, but the object is still there. Okay. But then like the garbage collector in Python and Java, what they will do is they will find those objects and they will clear them one by one. Okay. That's called garbage collection. So yeah, so that is there in Java and everything, but in C++ you don't have that. Why? Performance. So the garbage collector it acts at some overhead and it slows down the program a little bit. But C++ it's all about performance, so they don't have it. But now into C++ 11 you have a feature which can behave like that. Okay, so this is like a very thin wrapper around the normal pointer. Okay, normal pointer. It's called shared pointer and a unique pointer. And the idea is like when you say a unique pointer, okay, this is a type def. Okay, this is just a type def. That is, instead of typing all these things, std, standard pointer, motor, I'm just saying this one. Okay, you can rename types that way. All right. So you can say type def int my int or whatever. All right. So okay, so this is how you create a shared pointer. What you say is inside here you pass your new object. Okay, so you do a new and you pass it inside the shared pointer. All right. And if you pass it inside, then you don't have to worry about deleting it. So what happens whenever the pointer goes out of scope? Okay, the object will be deleted automatically. So how is it done? Because there's a reference count inside, and whenever you copy the pointer, it remembers it, and whenever that goes out of scope, it deletes it. Okay, it decrements it, and when that reference count goes to 0, the object will get deleted. So that's how it works, and that's quite good. So like, okay, the difference between unique pointer and a shared pointer is like the unique pointer is when it goes when the object goes out of scope, the braces, it gets deleted. So if you're going to share it, if you're going to pass a pointer, the smart pointer inside a function, and if you're going to give that pointer to anybody else, any other functions and stuff, don't use unique, use shared. All right. So otherwise you can simply use unique. All right. All right. So now the next one, the last topic is like duck typing. And yeah, so like I'll finish quickly. Okay. So what is duck typing? Now let's say you want to write a function that moves a robot forward. All right. So now previously we wrote functions where you can rotate one motor forward, right? So here, like, let's say a robot has multiple motors. Okay, like there are 6-wheeled motors and a 6-wheeled robot and like multiple wheels. And let's say all the wheels are independent. So there are some motors, robots like that, where all the wheels are independent. Okay. So in that case, like if you want to move that robot forward, you have to move all the wheels forward, right? Okay, spill all the motors forward at a certain speed, right? If you want to do that, now let's say like I want to write a function for that kind of a motor. So what can I do is like now the problem is like like it'll be very simple if there's only one kind of motor in the robot. If you have only H-bridge, no problem. Okay, you can simply write a function, pass the H-bridge class into that, object into that, and you can run the forward function, no problem. But let's say you are writing a library for a robot and you want to handle different types of motors also. Say H-bridge motor, simple motor, serial motor, like different types of motors. So like say there are 2 types of motors. Okay, both have like different signatures. Here it takes PWM and here it doesn't take anything like that. So that's Python code, this C++ code, right? So in Python, there's absolutely no problem. Okay, so that's something we like in Python. We don't think about types a lot. Okay, so why? Because Python has something called duck typing. Okay, duck typing means if it walks like a duck and if it quacks like a duck, it's a duck. What does that mean? That means like if you have a class, if you have an object, it has certain functions. If your object has a forward function, and if you're only going to use forward function, no problem. It doesn't matter what the class is. As long as that class has a forward function, there's no problem. All right. So here I'm going to write a function, and that function is only using the forward function, forward. So because of that, I can pass any kind of motor. I can pass this motor and I can pass this motor into this, and no problem. It will work. So that is duck typing in Python. But in C++, that won't work. Okay. At least until C++11, it didn't work. So the problem is like C++ has static type and is very strict with types. So you can't just create a function with one type of argument. Okay. And you can, so this is one type of argument and this is another type of argument. And you can't just pass the same, pass a different class into it, even though the class has like same function, similar functions with same name. You can't do that. Okay. So yeah, so that's a problem with C++. It was, and now it's not. All right. Let's see how to solve that. So that means now our objective is to create a forward function which can take any type of motor. It can take simple motor, H-bridge motor, or any other motor. All right. So now these are the templates. Okay. So yeah, now let's see here. You don't have to think too much about it. So it's like H-bridge motor, and the H-bridge motor has two, like it has one function, forward function, which takes speed. So this is a simple motor. So what's a simple motor? Like it is just say just a PWM pin where you give a voltage, where like you send it through a transistor, you amplify the voltage, and then you give it to a motor. Only that. It doesn't have any direction control. It doesn't have pins, those things. No, nothing. Okay, you just give a speed, it will work in that speed, and it can't go in reverse. See, it doesn't have a reverse function, and this may have a reverse function, but that doesn't. Okay, right. So that's a simple motor. This is H-bridge motor, but both have a forward function which are identical. Their signature is identical. Okay, what they do are different. Okay, so this is digital write and stuff, and but the signature is identical. It is returns a void and int speed, and it's forward. Right. So now, so this is like a good example for duck typing. I want to create a function which can take both type of objects. Okay, both type of classes. So for this is how I do it. I use template. Okay, so in a template, I say this is a type. It's like a placeholder type. Okay, it's a type, and then I'm telling the input is actually a pointer array. So that's an array of this many motors. This many motors, this number of motors, and I want to send all of them in this speed. So let's say I am giving an array of 6 motors. Okay, but what motors are they? Motor H or motor simple? I'm not telling. All right. So that is the beauty of templates. Okay, and I'm saying motors I dot forward. Now when I use it, what I do? Okay, when I use it, what I do? I can simply use it more forward. I can simply give this this array, or else I can simply give the other array. Okay, it doesn't matter. To the same function, it will work. Okay, so how does it work? So that is basically duck typing, right? Like you give the same you give any kind of object into this function. As long as it has forward, it will work. All right. Okay. So how does it work? Like all these are checked in compile time. So what C++ is doing is it's actually creating multiple copies of this function. Okay, so every time like when you're compiling, it knows that okay, you're calling this function with this particular class. Okay, then it creates a copy of the function with that class interface. Then it creates another copy of the function with another class interface. Like that, it will do everything for you. Okay, so that's called a template, right? So next one, okay, so I told you like Python has this lists and dictionaries. Okay, and you are familiar with that. And so C++, like you have arrays which are very restricted. You can't add stuff to the array, you can't delete, so you can't add something in the middle. Okay, so that's very clumsy. So instead of that, you have something like a list. You actually have a list. and you have vectors, and you have dictionaries in C++ too. So how do you use them? So this is how you use them. So they are called STL containers. So STL means standard template library. All right. So everything, all the containers like in this library, they are templated. So what we just saw earlier. So which means you can create these lists with your own classes. It doesn't matter. Okay, right. So yeah, so sometimes like when you're studying data structures and algorithms, you might implement this doubly linked list. Okay, so linked list and everything yourself. But then you don't have to actually, when you are doing actual development, when you're writing actual coding, you don't have to bother developing any of that, because they already have some very optimized stuff, okay, as libraries. So basically std list is a doubly linked list, right? You can just take it and use it. Okay, then all right, so how do you use it? So this is a class just for demonstration purpose, and here this is how I create a vector. Okay, std vector, and the vector's type is a motor, the element type is motor, and I'm creating a vector, and in a for loop dynamically, it doesn't matter. Okay, you don't have to do it in the compile time. So dynamically you can push a value over there to the back. Okay, push back means you are appending to it. Okay, it's like list, you are appending something to the list in Python. You can do the same thing here, and then you can you can remove values from it, you can check the size of it, then you can go to the front, you can go to the back, then you can insert something to the third element, you can insert this element to the as a third element, then you can erase the second element, then you can run this for each loop. Okay, so I showed you before, like for each, for motor in motors. Okay, for motor in this vector, for each motor you can run a for each loop, and you can print the stuff. It's just like in Python, right? So it's very very readable and very like handy. Yeah, and you can empty it if you want and everything. So this is a vector. So similarly there's a list, but like, so list means like, so vector is something like contagious, and like when you add and subtract and everything, it takes copies. So if you're adding something to the middle and removing something to the middle again and again and again, it's not a good thing. Okay, so it's not good for in vectors. But yeah, so in that case, it's better to use list. All right, so if you're adding and removing stuff, it's better to use list a lot. Yeah, so so it's contiguous. Vectors are contiguous. These lists are not. Then you have what stacks, queues, and sets. So that also you can use. Okay, so if you want a queue, okay, if you want a stack, you can just take the values, take the containers from STL containers and use them this way. All right, so this is a map. So that's a dictionary. Okay, so here I'm inserting a key pair value pair. Okay, I'm just writing a okay, so map and pair are two, map and pair are two type def, and then I'm adding stuff. I'm going through each of them in a for loop, and I'm printing stuff and everything. All right, so okay, then I think we are at the end. All right, so I just want to mention this one before we end. So that's like interrupts and callbacks. So I'm not going to demonstrate them. So the idea is like when you are doing microcontrollers, when you're programming microcontrollers, then like you need interrupts in many situations. So that is like if you have a certain sensor and you are running some big code, okay, and one way of doing that is you can check the sensor one by one again and again. Okay, so you can check whether somebody has pressed a button again and again. But then that is not good, because every time you check, you are like wasting time. Okay, one. The second one is like now if somebody presses a button when your code is running. Okay, so when like if you have a big code like a robot code or something, and while it's running, if somebody presses a button or if something happens, then you will miss that completely. All right, so because of that, you want something called an interrupt. So interrupt will trigger a function when there's an external event. All right, so when some pins goes high, or something goes low, or something happens to the pin, what will happen is like you are running a long program, that long program will be paused immediately, and a certain function will run. And you can specify which function. That's called the callback. Okay, you can specify that, and that will run. And then, like when that function finishes, your main code will resume. All right, so they are very handy, very useful, and yeah, so very useful. And you can actually have interrupts of multiple priorities. So you can have high priority, medium priority, low priority, like that. So what happens is, like the high priority interrupt can interrupt the low priority interrupts. Okay, so what does that mean? You have a main function running, and so something happens, a low priority interrupt happens, and the low priority code is running. Okay, the interrupt code is running. While the interrupt code is running, if there's a high priority interrupt, then the interrupt code itself will stop, and the high priority one will happen. Okay, you can do those things also, like higher order stuff. And yeah, so I have put some tutorial links here. You can just go there and you can follow those things in Arduino and in AVR. Okay, so we are done. So like okay, so back to the slide which I showed in the beginning. So these are like the key features which I wanted to highlight. So the classes, they have like zero overhead, and you can actually do all kind of things. Like you can do inheritance, subclassing, encapsulation, polymorphism. So if you know OOP, okay, so I think like it is very bad to learn OOP through C++. Okay, because C++ is already a complicated language. If you don't know OOP, it's better you learn it from Python or something and come here. All right, and if you know OOP from some other language, you can directly apply it. All right, so everything you do with Java, like Java or C, Python, you can do it here, and you can do more. All right, so yeah, then you have garbage collection like things. Those are the the smart pointers. All right, so you have smart pointers, and you have you have for each loop, which makes it readable. Okay, so like you don't have to write int I equals this one, and then you write like the size, and then you iterate over it. Like you don't have to do. You just say for min motors. You have dynamic containers, list vectors, map dictionary. You have everything. You have duck typing. All right, so you can write very efficient, very clean, very readable code in C++ than before. All right. Okay, so thank you so much, everyone. All right. So yeah, thank you so much, everyone. So if you have any so questions, please keep asking. I'll be here. Ask in the Telegram group. You can ask later, or else right now you can ask and give you a feedback. Okay, so you can like go to this form, the forms, and give feedback. All right. So before I hand it over to Dr. Subodha, I will mention a couple of references which you can follow. All right. So this is the first one. This is something I like a lot. It's a YouTube channel, and you can just like when you're procrastinating, when you're not doing anything important, you can just watch it. So like this guy is a video game developer. So and from he talks in the point of view of video game developers. So then he's using all these containers, the C++. Okay, so he's talking about C++, and he gives a lot of demonstrations. For an example, he goes into memory and shows the things and everything, and like how to write very optimal, very clean code. And he introduces all these concepts like templates and like basically everything you want to learn, you can just go there and see. There are like a lot of videos. I have given the playlist. Then Geeks for Geeks, it's a C++ article series. Okay, and then there's a good book, a tour of C++, by so this guy. So he is actually the founder of C++, the guy who created the first C++ compiler and defined C++. Right. So he wrote like this book, and it's like a highly acclaimed book. So I have yet to read it, but you can if you're interested, you can check it out. All right. Then for Admel programming, I found this is a very good tutorial. So it's like a step by step how to do it. Okay, if you're programming Admel chip, how to make the support circuit, then how do you flash it, like how do all those things. Okay, everything step by step is there. And similarly, like Admel programming, so that's like you have tons of way to program a chip, right? Serial programming, ISP, and everything. So this is the official guide, all right, for the Admel's guide. So you can check that out also. Okay, so yeah, thank you so much. And I hope sir is there. So, yeah, so Dr. Subhadra is there. So I will hand over to him. Yeah. So thank you so much, everyone. Please give your feedback. All right. So we value that a lot, and we'll be using that to improve the future sessions. So please give the feedback and before you leave. Thank you. And please go to the link and ask any questions. I'll be here. All right.
I hope I'm audible and you can see me. Right. Perfect. I'll take about 30 more minutes and then we'll wrap the session up. Before I get started, I'll start from where Abba left off, the feedback. So I've shared it in my screen as well, and we'll put the link in the chat. So the feedback is very important to us. We did the 4 workshops free of charge for everyone. And in addition to the time that we spent conducting the workshops, during the week, we spent another good 4 to 5 hours discussing what the content should be. So our motivation was that everybody's at home during the pandemic, and some students who are in schools and who are waiting to enter the universities, you are going through a tough time because everything is closed and it's not very easy like learning in person. So we wanted to contribute the best we can with the knowledge that we have. So that was our entire motivation. So this feedback is the only thing that we'll get back from you. So please make sure that all of you fill the feedback form. We'll send the same in the Telegram group as well. So we highly value all the feedback that we can gather. Right. With that said, let me move on to the session for today. I'll first turn off my video so that the internet connection would be stable. And let's see. Okay. It's the final discussion of the workshop series we had. So today we'll be, during the final 30 minutes, we'll be touching on the embedded system design flow and also what you can do next. Now that you have this knowledge, what comes next? So we started the session, the workshop series, by showing you the applications of embedded systems. And during that time, I told you that there are so many applications, starting from automobile all the way up to the handheld devices that you're using. So now you might be wondering, how do I go from developing the Medibox? How do I come to developing products in these domains, right? And I broke these domains down into 4 major components. That is computer architecture, programming or software, communication, and enclosure design. Okay. For those who were not with us during the first workshop, I'll quickly recap. So computer architecture is the brain behind the brain power behind all the embedded systems. If you look at the microcontroller or microprocessor, people design those things. So that is the science, designing those things. That is the science behind computer architecture. So what you did was, during the workshop series, is to take a microcontroller that was already designed and you programmed it. Because unless you tell the microcontroller what to do, it doesn't matter what capabilities the microcontroller or the microprocessor will have, it will just sit there without doing anything, right? So the computer architecture people will design the microcontrollers, the hardware that goes inside those chips, and you as programmers, you program those microcontrollers and made it work. You told the microcontrollers what to do. Okay. And the third aspect is the communication part. We did not touch upon this a lot. We only discussed about UART and ISP briefly. But apart from that, there is a whole another domain that if you are interested in learning, things like Bluetooth, Wi-Fi, how do this communication happen within the chip? Because if you open the chip, there is communication going on inside the chip as well. UART and I2C, those things allow the chip to communicate with other peripheral devices, things like your LCD and other devices if you connect them, right? So there are different domains starting from inside the chip, peripherals connected to the chip, and then these Wi-Fi, Bluetooth, and all these technologies. So communication is another whole different paradigm for you to learn and to master. And once you put everything together, of course, if you are building a product, it has to look nice. Otherwise, nobody will buy it. I don't think anybody will go inside a device and see, oh, the electronics is fantastic, I like this, and then buy it. No, people buy a product because it looks nice in addition to its functionality, right? So because of that, enclosure design plays a huge role. There are design engineers, tools like SolidWorks used in the industry that will help design these beautiful enclosures that the consumers would love. So with these 4 main pillars in mind, we started with the Medibox design. Okay. So during that design, what we did was, first of all, we had a concept. We had the concept of developing a tool that day-to-day people can use so that it will be a reminder for them to take their medication. Once we had the concept, we specified. We had an LCD, we had lights blinking, alarms going off, right? That was our specification. This is our product. We are building our product so that the product adheres to that specification. And then for the specification, we told you that these are the hardware components that you can use. Of course, you can implement the same Medibox with so many other hardware and software options. We went with Arduino and the list of items that we gave you, but it doesn't mean that is the only option, right? So with your knowledge, you will understand that there are alternative options. But in our case, we told you that we are getting started with Arduino and the Arduino IDE, and which C++ comes together with it, right? Then we went ahead and implemented. In terms of hardware, we assembled the hardware that we had on a PCB. We wrote the software, we compiled it. I hope you are familiar with this word by now. And then finally, we combined them together to come up with the Medibox. And during that process, we did not forget to validate and evaluate as well, because what this basically means is that once you press a button, it should do what it's meant to do. So we tried and tested whether the device is working as we intended to do, right? So this was the overview of the process that you followed. Okay, I just wanted to give you the big picture of what happened in Medibox so that you can relate this to another diagram that I'm going to show you in a while. That is the typical embedded systems design process. So this diagram is specific for Medibox. So during this process, you went through these learning outcomes. So I just wanted to show you now. I showed this in the beginning in the very first workshop as well, so that now you can see whether you actually understand these things. The basics of how a microcontroller works with the I/O framework. We did programming, we did simulations, and then towards the latter half of the workshop series, you got an in-depth understanding of microcontrollers. Second and third workshops, we learned how to design a PCB and also how to manufacture one. Then finally, we combined all of those learnings together to build the Medibox. Today, you looked at the previous session conducted by Abba. We touched on the advanced features on C++. So if you are planning for the future, that will be very insightful for you. So this is what we are doing right now, describing the embedded system design process. So I hope by the end of this session, in another 30 minutes or so, you would have accomplished all these learning outcomes through our workshop series. Of course, the recordings are available online. You can go back and refresh your memory, but this is what we achieved during these 4 weeks. So congratulations for everyone for making it so far, this far in embedded systems. That's a huge feat. You guys were with us for 4 consecutive workshops. So what's next? This is my main focus of this 30 minutes. What can you do next? So here are some tips for you. First of all, you build the Medibox with us, but if you're looking ahead at the future, it's important that you get your hands dirty on something new. You only learn by doing. There is no other shortcut. You can only learn by doing. And the way to do that is to build on top of what you already know. You can strive to be better than yesterday. By now, you have a certain set of things that you learned. What is the immediate next step that you can take? So that I'll briefly tell you. What can you do to build on top of what you already know, right? First and foremost, because we started off with Arduino, there are what we call Arduino shields. This was touched upon during the workshops as well. We only had the LED and the buzzer and the lights and some push buttons, but there are other capabilities that the Arduino can offer. For example, if you want to connect the Arduino to the internet, there are things like Ethernet shield, right? So you can plug in a cable and then your Arduino will be connected to the internet. Then you can communicate with the cloud. Then you have things like motor shield. So if you can remember Abba's example from the C++ session, we were controlling motors. So to make things easier, there are motor shields. And then you can integrate other sensors, things like smoke detectors, humidity, temperature, whatever the physical parameter that you can think of. Most likely, there will be a sensor that can capture that physical parameter. Then we have other kinds of input devices. So we talked about push buttons during the Medibox, but you can you have fancy things like a joystick if you want to control something. Maybe you're controlling a car with your Arduino. You have a joystick shield, right? So there are so many other shields as well. I'm only listing a few, like touchpad, another input device, GPS if you want to record the location, GSM if you want to do cellular communication. This is pretty good. Then you can even have a camera if you want to take pictures, maybe do facial recognition, that you have shields for that, right? So all these things, that is one of the next steps that you can do based on what you already learned in Arduino. Okay. So once you have a firm grasp of these Arduino related technologies, you can even go and develop these PCBs by yourself. Say, for example, you don't need all the capabilities within an Arduino. You don't need all the pins. Then why not come up with your own PCB? We told you how to develop a PCB. You can look at the schematics of these shields. For example, if you want to develop a GPS tracker, you can take an Arduino, plug in the GPS shield and program and do it. But on the other hand, you can do a custom PCB. Check the hardware components, design your own PCB, and maybe you can come up with a smaller GPS tracker, right? Because you like the GPS tracker to be as small as possible for ease of use. A custom PCB can help you, right? So we gave you the necessary tools and tips for you to get started on all those things. Okay, so now I'm moving on to something that we did not necessarily teach you. Once you're familiar with these Arduino technologies and all the custom PCB designs, the next step that you can take from that point onwards is to explore the world of single board computers. So what's the difference between a single board computer and an Arduino? Mainly, this has more computing power and more resources. So this little thing over here is capable of loading an operating system and connecting peripheral devices and doing so many other stuff, right? So it's on one board, it's pretty small. The size can be comparable to an Arduino. There are bigger boards as well. In 2021, there's an article you can Google from this title. There's a very comprehensive list of all the single board computers available in the market that you can get and play around with. Things like Raspberry Pis, NVIDIA Jetson, BeagleBone, those are all available. So let me help you a little bit more and tell you what kind of applications you can think of using single board computers. First of all, there's a very popular topic. Well, all three are popular topics these days, but you might have heard the words machine learning and artificial intelligence a lot. There are single board computers using which you can implement those things. For example, the NVIDIA Jetson is a very well-known SBC, single board computer, to implement machine learning. And there are variations of Raspberry Pi, Raspberry Pi 4, that is another popular SBC to implement machine learning, and Odyssey is another SBC. Internet of Things, there is an SBC called NodeMCU, Raspberry Pi, BeagleBone. These are all fantastic, good fits for Internet of Things. So this Odyssey is a very powerful board. So here, things that you need to consider is the capabilities given by these SBCs and the cost, right? Check how much that costs. So Raspberry Pi is a very cheap option. So is the NodeMCU. So depending on the application you need, Google these devices, see what capabilities they have, and pick the one that is cheapest for whatever your application is, right? And then finally, you have things like robotics. For robotics, you have the Raspberry Pi 4, the BeagleBone, and the Odyssey. So this is not an exhaustive list. If you Google, you will find other SBCs as well in the market. But I just wanted to tell you that these options are available, and some SBCs are better suited for certain applications compared to the others. So we wanted to give you a guideline as to what the options are, so you can get started. Excuse me. Right. So now that you have that overall idea, let me show you a couple of videos, things that people have done, projects that people have done in the past that you can get some inspiration from and try to implement on your own. Let me reshare after optimizing for video. Let's see. Okay. Okay, so in that video, we saw a bunch of things, right? Robotics, and then there's a question in the chat asking to share the slides. I have uploaded the slides in the Google Drive, so you can access all the links through that Google Drive. Okay, so in the video, we saw a bunch of things, starting from robotics to there was a security system, facial recognition, gesture recognition system. Whatever you do with your hand, the system understands and acts accordingly, right? So all these things are possible through single board computers, and some of them are even possible through things like Arduino, right? So remember, the only difference is the architecture and the tool set will be different. But on the other hand, we are only talking about a difference between the capabilities of the two devices. If a microcontroller, which is less resourceful, is not able to do a certain task, a single board computer will be. Right? So that is why I said, depending on your application, there are different options available to you. And even within single board computers, there are different capabilities. So I gave you a list, check them out, check the devices, and then you'll understand what is best for your given application. I'll show you another video. This one, so the video that I showed you a while ago, that is specific to things that you can do with a Raspberry Pi. That's a SBC that I introduced. Let's move on and see a video related to Internet of Things, because we are talking about connectivity, connected devices. You all have your mobile phones, and you might have a smartwatch. Maybe you have some devices, some other devices within your at home or your workspace that is connected to the internet. So it's a very popular upcoming area. So let me show you something that you can do with a microcontroller developed by Texas Instruments. Texas Instruments is a well-known player in the embedded systems domain. So let's watch this video as well to get an idea.
Let's take a look at a typical day in a world connected by SimpleLink MCUs. As you leave your home for the day, you can use your phone to lock the front door using a Bluetooth low-energy connection. The lock reports its status back to a central security panel with a Zigbee or Thread network. The panel aggregates data from door and window sensor nodes throughout the home using the ultra-low power sensor controller, which monitors sensor inputs while the main MCU sleeps. The system can now monitor for home intrusions while you're at work, all operating on a coin cell battery. The data can even be sent to the cloud so you can control your system from anywhere in the world. At the office, a central thermostat collects data from sensors throughout the building using a sub-1 GHz network, and using that information, communicates with the air conditioning and heating unit to adjust the climate in each room. The expanded memory and concurrent protocol support of the wireless MCU allows a technician to use their smart device as a remote display. That way, they can interact with the thermostat over Bluetooth Low Energy while the system maintains the sub-1 GHz connection with the temperature nodes. Outside the office walls, metering sensor nodes around the city monitor water, gas, and energy usage, and transmit data to a central point over an even longer sub-1 GHz network using the integrated ultra-low power PA. At the job site, equipment can warn you that it's about to break down. The health of these machines is being continuously monitored by analyzing tiny vibrations using an integrated precision analog to digital converter. One investment in the SlimpleLink software can help you connect the home, building, factory, and city fast. Please visit ti.com/SlimpleLink for more. SlimpleLink, what will you connect?
Right, so that I hope gave you another set of ideas which you can explore. It showed you how to connect your some of your thermostats, maybe your home security system to the internet, and also monitor the health of devices in a manufacturing environment. So all these are possible through these embedded platforms, right? So if you Google, you'll see a lot more other videos on the internet as well that highlights things you can do. So with the knowledge, build gradually and come to a point where you can try these projects out. Right? So that's what we hope that you will do without stopping from the knowledge that you have. Why don't you try out some of these things as well? And so it's not the immediate next step. I explained that we have the Arduino shields and the custom PCB stuff. Be familiar with them, and after that you'll be comfortable to move into the domain of SBCs, single board computers. Right? So it's up to you. Okay. Let me give you some more tips, and before that I'll reshare without optimizing for video so that you can save your bandwidth. Okay, I hope you can see the slides without any issues. Moving on. So I told you to get your hands dirty with something new, build on top of what you already know, right? And the next one I can tell you is that these projects that we just showed you might look overwhelming. You might be thinking, I only know how to build the Medibox. How can I go from there to here, right? So you learn by doing, of course. And if you look around, there are tons of resources, both on the internet, and you can get it from your peers as well. Abba, I stopped playing the video. Sorry, the question that you asked in the chat. I can't see the video playing. Right now I'm sharing the slides. Can you see the slides?
I can see the slides.
Okay, thank you. So if you think that the projects are overwhelming, it might be in the beginning, but once you learn and move forward, it will start making more sense to you. Let me give you a few resources that you can follow. There are so many online courses like Coursera, Udacity, Khan Academy. So these are all websites through which you can get free online education, right? And then YouTube is also a fantastic source. It's not an online learning platform per se, it's a video hosting service, but there are so many channels within YouTube. Content creators have added tons of content related to embedded systems, the projects they have done, and all that. So go through these resources, check out the courses, what they have to offer. If you find something interesting, some courses are free, some courses you have to pay for them. So depending on your financial situation, you can choose what to go with. Check the curriculum, what they're going to cover. So if you think that is a good fit for you, depending on what you already learned, then go for it. You can binge watch just like you binge watch a TV series, and then select some of the courses that are very suitable to you. Okay. Right. Then, and of course, in addition to that, if you get a degree maybe in electronics, that's definitely another tool, another avenue for you to learn. But even if not, education is right now available to everyone. You just have to access the internet. So it's pretty straightforward. You just have to know where to look and what to pick, right? So for that, you will need to stay connected with the community as well, because if you have a question, maybe there are people who did this before you. Maybe they can guide you. That's the whole purpose why we had the Telegram group and the Facebook group. Stay connected with them. We have posted the links in almost every flyer that we added and in the chat as well. Stay connected with the communities, because collaboration always helps to learn new things. If you have a question about a course that you found online, you want to take it, but you're not very sure what you will learn, then maybe there is someone else who will tell you, right? I have taken this. This is really good. If you know this, you can do it. Otherwise, maybe the course is bad. Don't take it. So staying connected with the community can really help. Then once you are familiar with the basics, you can start to learn advanced concepts. Once you are familiar with Arduino and SBCs, building your own PCB, there are even more advanced concepts that you can learn. Let me tell you briefly what they are. I don't want to go into details because you have a basic understanding at this point. If I give you a lot of details, you might be confused. So let me give you a very brief overview about what I mean by advanced concepts. For that, let me take you back to the embedded design flow. So I told you the design flow that we followed in the Medibox project, but in general, if an embedded engineer is approaching a given problem, what will he or she do? So it's typically not one person, it's a group of people. That's how all these big companies work. What is the design flow? So let me give you an overview. First of all, the concept, it is the same, right? You have a product that you want to build. How do you build that? You first conceptualize it. And then this step is also similar to what we did with the Medibox. You specify. And the only thing I want to highlight here is that when developing the Medibox, we basically told you what to do, right? We told you that these are the functionalities. The LCD should work. When you push buttons, there's a menu. So we used our natural language, right? We told you what to do. But if it's a large and complex design, you don't usually write those things in natural language. I mean, in English, Sinhala, Tamil, whatever, we don't write using our spoken or written languages. There are special languages developed to capture the specifications. One example from something you already know, you can write the specification as a C or C++ code. Right? That's one way of doing it. And there are other models that the industry has developed and academia has developed. Things like finite state machines, state charts are available, right? So I'm not going to give you a list of things. If you Google for specification languages, you will find a bunch of things, but those are slightly more complex things. So I would only advise you to go into that level of detail once you are familiar with all these Arduino, PCB design, and Raspberry Pi, SBC kind of things, right? Because this is the way that somebody will develop a microcontroller found in your Arduino. Right? So now we are zooming in and talking about more complex concepts. So don't try to get started from there. You will be discouraged. Right? So go step by step. That's always the best policy to follow. So once we capture the specification through a very specific specification language, we have the same story as before. The designers will tell you, these are the hardware components available to you. These are the software components available to you. With that information, you move on to the next step. This is similar to the implementation, but there is a slight difference in complex embedded devices. I'll tell you what the difference is. So earlier, I told you we are assembling hardware, right? But another option, if you're going for a very complex system, companies like Apple, Samsung, when they develop their iPhones, they have to design the hardware as well. So they don't really get the hardware from the market always. They design their own things. If you look at an Apple phone, the chip inside the Apple device, it's manufactured by the company itself, right? So in addition to assembling, they do what we call synthesis. So this is a process. Just like you write a code and compile that and put it as software, you write a code and you synthesize that as hardware. If you have heard things like words like FPGA, that is what we do through those programmable devices. And then once you design, you manufacture that on a chip. This process is commonly called fabrication. You put it on silicon. That is how you get the microcontrollers that you have worked with, right? If you look at your, well, you cannot see it if you look at your laptop, but inside your laptop, you will see most probably an Intel chip, right? You've seen the logos, Intel inside, Core i5, whatever, that is the chip. So that hardware is designed by someone, and that process we call in very broad terms synthesis. There are other details in here as well, but I just want to tell you, in addition to assembling, you can manufacture your own hardware. And the reason why I have this this kind of balance here, and I said the hardware software partitioning, is during these complex design processes, people will decide, okay, I want to have this functionality implemented in hardware. I want to have this implemented in software. So whatever you want to do, the design engineers will decide, do I need to manufacture a brand new hardware for this? Or am I going to buy something from the market and assemble? Or am I going to have this as a program running on a microprocessor that I can program, right? So some of these hardware devices will be manufactured for a very specific purpose. So in your microcontroller, you could program a lot of things. You can write to an LCD, you can blink an LED, you can get a sound out of a buzzer. All those things were possible. But there are some cases where you manufacture a hardware for a very specific purpose and it can be used only for that. And the reason for doing that is then that hardware is really fast. It's not like general purpose. It's for a very specific purpose. Therefore, it is really fast. If you have a very safety critical application, for example, let's say it's a self-driving car, right? So time is of the essence. For your Medibox, you didn't really worry whether you pressed a button and it took maybe 1 second to appear. You didn't really worry, right? But if it's a safety critical application where microseconds can be a matter of life and death, then the speed in which things happen is really critical. So for such instances, people tend to go for hardware specific implementations. That's one reason why people will go for that. Right? So during this implementation stage, the embedded design engineers will estimate, explore, and do the partitioning, and then decide the final outcome of the device. So there are tons of things going on here. This testing, estimation, and validation kind of thing, it happens in each and every step during the design process. You do the design, you take the specification, you do the design, and then you test the design whether it matches the specification. Then you implement, and then also after you implement, you test. So there are different testing stages. Before you implement, you estimate, because you have not implemented this, you don't know how it's going to perform. So you estimate even before manufacturing to make sure that your design is correct according to the specification. So all these steps are there when you design a complex embedded system. I hope you get an idea about what happens in large companies when you design complex embedded systems. But for now, you can get started from the knowledge that you have about Arduino and slowly move your way up to all these complex concepts if you like to do so. Okay. But even though this will look overwhelming, this same breakdown of computer architecture, programming, communication, and design applies to this process as well, right? So if you want to master any one of these aspects, you can be a valuable contributor to this design flow, because these things are not done by one person. It's a group of people. It can be tens, 20s, hundreds, 200s, depending on the complexity of the device. So whatever you like to master, if you learn them and master, there are so many opportunities out there in the world, so many global companies. Don't think it's a dream for Sri Lankans to work in these big companies. Of course, there are leading companies within Sri Lanka as well, but in the global stage, you have heard these names. It's not an impossible task. There are so many Sri Lankans currently working in these places as well. So it's up to you to learn and master, and either you build your own or you become a valuable contributor to one of the global or leading local players within the country. With that, the final piece of advice that I wanted to give you is that there are no shortcuts. The University of Moratuwa has the electronics and telecommunication degree that goes on for four years, right? So there's a reason why it goes for 4 years. There's a lot of things to learn. I am not saying that to develop a product, you need to spend 4 years, but the degree will give you the basics about each and every aspect. So it takes time. But even if you want to learn only the things required to develop your product, it will take time. I don't know how long, maybe 1 year, maybe 2 years, maybe 6 months, depends on you and the amount of time that you can put in. But the message here is that there are no shortcuts. If you want to reap the rewards, you need to put in the effort. And one of the things that I personally follow is that you learn something, you learn by doing, and you keep repeating. Then you become a master of whatever it is that you are interested in. Of course, you cannot do that for each and everything that you are interested about, but whatever domain that you choose to follow, you learn, you memorize, and then you repeat. In today's world, where there are so many resources on the internet, you don't even have to memorize. You only have to memorize where to look or write it down. Then you can always Google, see what the options are, and then learn, right? But being engaged in something and then repeating that will make sure you master whatever the craft that you're following. Okay, so with that, we can wrap up for today. Before that, I wanted to express our gratitude for few people that followed us or helped us throughout the process. First of all, the speakers from the Department of Electronics and Telecommunications Engineering at University of Moratuwa. All 6 individuals spend a lot of time preparing the slides, discussing what's best, deciding the flow of the workshops, and then delivering the content. Then our partners who made all these possible, IEEE, SLInspire, and the Career Compass projects within IEEE. All the live streaming, the designs, publicity was handled by them. They gave an introduction in the beginning of the workshop series as well. So thank you for all the support during the 4 weeks. And then finally, we had supporters throughout the process here and there. Magic Bit, Circuit Breakers, in which Deepana, Charlotte, and Dilanka are members. So they helped a lot being presenters and also creating content. Zone 24/7, a leading embedded systems company in Sri Lanka, helped us giving slides and resources. Shout out and ULead, who were responsible for the messages, the text messages that you got. And so thank you, a huge gratitude for them as well. And last but not the least, thank you for being such a wonderful audience. We hope you extracted something from this, and we hope you will stay engaged and learn and be interested followers of embedded systems like we are. And then finally, I'll leave you with this word of advice. Thank you again for everyone for all your efforts. We really appreciate it. Please give us feedback. That is the one thing that we really value from you, in addition to you continuing in this journey of embedded systems and achieving great things. Yeah, that's it. So we'll wrap up. Thank you for being with us for 4 weeks. Thanks.